There is a photograph of Paul Dirac standing at a chalkboard in Cambridge, his handwriting so small and precise that colleagues sometimes needed magnifying glasses to read his equations, and in that tiny script lay some of the most profound descriptions of reality ever written by a human mind. This is a story told slowly, in the manner Dirac himself might have preferred, with long silences and careful words, about a boy from Bristol who spoke so rarely that his family ate meals in near total quiet, and who grew into a physicist whose equations predicted the existence of antimatter before anyone had ever observed it. If these narrations help carry you toward rest, a subscription means more evenings like this one, more unhurried hours spent in the company of remarkable lives. The year is 1902, a century just beginning, and in a modest house on Monk Road, a child is learning that silence can be its own language, and so we begin there. On the 8th of August, in the year 1902, in a modest terraced house at number 15 Monk Road, in the district of Bishop's Ton, in the city of Bristol, a child was born who would one day reshape our understanding of the very fabric of reality, though on that particular summer morning he was simply a small and rather quiet infant, wrapped in cloth and held by his mother in an upstairs bedroom while the sounds of the neighborhood drifted in through the windows, the clatter of horses on cobblestones, the calls of vendors, the ordinary symphony of Edwardian England going about its business, entirely unaware that anything of consequence had occurred. The child was named Paul Adrian Maurice Dirac, a name that carried within it the blended heritage of his parents, and he entered the world in circumstances that were neither grand nor impoverished but rather occupied that careful middle ground of the lower middle class, where respectability was maintained through constant vigilance and where every shilling was accounted for with the kind of precision that Paul himself would later apply to the equations of quantum mechanics. The house on Monk Road was a narrow building of red brick, one of many similar houses arranged in long rows that characterized the residential streets of Bishop's Ton, a neighborhood that had grown up in the latter decades of the 19th century to accommodate the expanding population of Bristol's working and professional classes. The streets were lined with young trees that had not yet reached their full height, and the pavements were swept clean by residents who took pride in the appearance of their modest domains, and the whole area possessed that particular quality of striving respectability that marked so many English suburbs of the period, neither fashionable nor rough, simply a place where families of limited means could raise their children in relative comfort and send them to local schools and hope that the next generation might climb a rung or two higher on the social ladder. Paul's father, Charles Adrien Ladislas Dirac, was not himself English, a fact that set the family somewhat apart from their neighbors and contributed to a certain social isolation that would come to define the household. Charles had been born in the canton of Valais, in the French-speaking region of Switzerland, and had made his way to England as a young man, eventually settling in Bristol and securing a position as a teacher of French at the Merchant Venturers Technical College, an institution that provided practical and vocational education to the young men of the city. He was by all accounts a capable teacher, respected by his colleagues and students for his command of his subject and his exacting standards, though he was not a man who inspired warmth or affection, being rather formal in his manner and precise in his expectations, qualities that served him well in the classroom but that created a particular atmosphere within the walls of his own home. Paul's mother, Florence Hannah Holton, came from rather different stock, being the daughter of a Cornish ship's captain, a man who had spent his life navigating the waters around the British coast and who had raised his daughter in that particular tradition of seafaring families where independence and practicality were valued above social pretension. Florence was a gentle woman, patient and nurturing in her disposition, though she found herself increasingly subordinated within her own household to the wishes and rules of her husband, who ran the family with a rigidity that left little room for spontaneity or warmth. The marriage had produced, before Paul's arrival, an elder son named Reginald Felix, known as Felix, who had been born in 1900, and it would produce after Paul a daughter named Beatrice, who would arrive in 1906, so that Paul occupied that middle position among the children, neither the firstborn nor the baby, a position that perhaps suited his temperament for quiet observation. Charles Dirac was a man who believed firmly in discipline and in the improvement of the mind through rigorous education, and he applied these principles to his own children with an intensity that bordered on the oppressive, creating within the household a system of rules and expectations that shaped the childhoods of all three children, but that fell with particular weight upon the young Paul. The most notable of these rules, and the one that would have the most lasting effect upon Paul's character, concerned the speaking of languages at the dinner table, for Charles had determined that his children would learn French to a high standard, this being not only his native tongue but also the language of culture and refinement in his estimation, and he enforced this determination by requiring that anyone who wished to speak to him during meals must do so in French, and in French alone, with no lapses into English permitted under any circumstances. This rule might seem, from a distance of more than a century, merely strict, the kind of educational discipline that many parents of the period might have imposed, but in practice it created a profound division within the family that left deep marks upon all the children and upon Paul most of all. For while Felix struggled with his French and Beatrice was too young to manage it at all, Paul was placed in the position of being the only child whose French was deemed adequate by his father's standards, and this meant that he alone was permitted to eat his meals in the dining room with Charles, while his brother and sister were relegated to the kitchen, where they ate with their mother and were free to speak in English. One might pause here to picture this scene, which repeated itself day after day throughout Paul's childhood, the father and the small boy sitting together in the dining room, the meal consumed in near silence because Paul, finding that his French was not equal to expressing the thoughts he wished to express and knowing that English was forbidden, simply chose not to speak at all. While in the kitchen his mother and siblings conversed in the easy, comfortable way of family, their voices perhaps audible through the walls, a warmth from which Paul was separated by his father's rules and by his own developing preference for silence. It was from this experience, Paul would later reflect, that he learned a lesson that stayed with him throughout his life, which was that talking was not necessary, that one could exist quite satisfactorily without the constant exchange of words that most people seem to consider essential, that silence was not an emptiness to be filled but rather a space in which thought could proceed unimpeded. This lesson, learned in childhood at the dinner table of a strict Swiss father, would manifest in adulthood as a taciturnity so profound that it became legendary among his colleagues and students, a quality that could make social interactions with Paul Dirac somewhat challenging for those who expected the normal rhythms of conversation, the give and take, the small talk, the polite inquiries about health and weather, for Paul had learned to dispense with all of that, to speak only when he had something of substance to say, and to remain silent, sometimes for very long periods, when he did not. The household at Monk Road was not a happy one, and this unhappiness pervaded the atmosphere like a faint but persistent chill that never quite lifted even on the warmest days. Charles Dirac had few friends, being a man who did not easily form attachments and who seemed to prefer his own company to that of others, and he discouraged visitors to the house, so that the family existed in a state of social isolation that was unusual even for that relatively private era. The children did not have playmates visiting, the adults did not entertain. The house was quiet in a way that went beyond mere peacefulness into something more like withdrawal, a turning away from the world outside that left the family enclosed within their own small sphere. Florence, who might in other circumstances have been a sociable woman, found herself confined by her husband's preferences, and the children grew up without the normal experience of a home open to neighbors and friends, without the casual coming and going that characterized most family homes, without the sense of being part of a wider community of connection and warmth. For Paul, this isolation was perhaps less burdensome than it might have been for a different kind of child, because from a very early age he showed a marked preference for solitary pursuits, for activities that could be conducted alone with a book or a puzzle, for the company of his own thoughts rather than the company of other children. He was not a boy who longed to play in the streets with the neighborhood children or who felt the absence of close friends as a painful lack, but rather one who found in solitude a congenial environment for the kind of mental activity that interested him, which was, increasingly, the activity of mathematics. Even as a young child, before he had received any formal instruction in the subject, Paul demonstrated an unusual facility with numbers, an ability to solve problems in his head, to see patterns and relationships that others might miss, to work through calculations with a speed and accuracy that suggested a mind peculiarly suited to mathematical thinking. This early fascination with mathematics was not something that Paul announced or proclaimed, for he was not a child who announced or proclaimed anything, but rather something that revealed itself quietly, in the way he would sit with a puzzle until he had solved it, in the way he would work through sums that had not been assigned to him, in the way his eyes would light up, or rather would focus with a particular intensity, when presented with a problem that engaged his abilities. He learned to solve things in his head before he learned the formal methods that schools would later teach him, developing his own intuitive approaches, his own mental shortcuts, his own ways of seeing through to the heart of a problem, and this early self-teaching perhaps contributed to the originality of thought that would later characterize his scientific work, the willingness to approach problems from unexpected angles, to dispense with conventional methods when they seemed cumbersome, to trust his own mathematical instincts even when they led him into unfamiliar territory. Books were his constant companions, and puzzles of various kinds occupied his attention, and he was content to spend hours alone with these pursuits while other children might have grown restless and sought out company. The neighborhood around Monk Road offered what diversions any Bristol neighborhood of the period might offer: the parks and open spaces where children could play, the shops along the nearby roads, the comings and goings of daily life. But Paul seemed largely indifferent to these attractions, preferring the interior world of the mind to the exterior world of social interaction. His mother, observing this tendency, perhaps worried at times about her quiet middle child, so different from the more outgoing Felix, so self-contained and so apparently content in his self-containment, But there was little she could do to alter his nature, and perhaps she recognized in his solitary habits a kind of contentment that was genuine, even if it was not the kind of contentment that most parents would have chosen for their children. The modest circumstances of the family meant that there were no luxuries, no holidays to the seaside beyond what could be managed on a teacher's salary, no expensive toys or elaborate entertainments, but for a child like Paul these material limitations were of little consequence, for the pleasures he sought cost nothing at all, being merely the pleasure of thinking, of solving, of understanding, pleasures that could be pursued in a small bedroom in a terraced house in Bishopston just as easily as in a grand mansion, and perhaps more easily, for there were fewer distractions, fewer obligations, fewer demands upon his time and attention. The years of early childhood passed in this manner, quietly, in a household ruled by a strict father and marked by isolation and silence, years during which Paul's character was forming in ways that would prove permanent: the taciturnity, the self-sufficiency, the intense inward focus, the love of mathematics, all of these taking root in the soil of his unusual upbringing and growing in the particular climate of that household. By the time Paul reached the age of 12, in the year 1914, he had become recognizably the person he would remain throughout his life, a person of few words and deep thoughts, a person more comfortable with equations than with conversations, a person who had learned in childhood that silence was not merely acceptable but preferable, and who would carry that lesson forward through all the decades that followed, through his education, through his revolutionary contributions to physics, through his fame and his honors, never quite losing the marks of those early years in Bristol, of the dining room where he sat in silence with his father while his mother and siblings ate apart, of the house where visitors were unwelcome and solitude was the norm, of the quiet rooms where a small boy with dark hair and serious eyes learned to find in mathematics a companion more reliable than any human friend. During the years of Paul's early education, the city of Bristol continued its steady rhythms of industry and commerce, though the shadows of a great and terrible conflict were beginning to gather across the European continent. Paul began his formal schooling at Bishop Road Primary School, a solid brick institution where children sat in orderly rows and learned their letters and sums in the methodical fashion of the Edwardian age. The school was unremarkable in most respects, offering the standard curriculum of reading, writing, arithmetic, and the moral instruction considered essential for young minds of that period. Paul attended his lessons quietly, as one might expect from a child of his temperament, and the teachers noted that he was diligent and capable, though perhaps not yet displaying the extraordinary abilities that would later define his life. The classroom would have been filled with the sounds of chalk on slate, the rustle of papers, and the patient voice of the schoolmaster guiding students through their exercises, and young Paul absorbed these lessons with the same methodical attention he would later bring to far more complex matters. The transition from Bishop Road Primary School to secondary education brought Paul to an institution that would prove unusually well suited to his particular cast of mind. The Merchant Venturers Technical College was not an ordinary school by the standards of the early 20th century, for it placed its emphasis squarely upon practical science and technical training rather than the classical education in Latin and Greek that dominated most institutions of learning in England at that time. This was the very same school where Charles Dirac taught French, and so Paul walked each day to the same building where his father held his professional position, a circumstance that must have created a certain inescapable pressure and proximity. The choice of this school was significant in ways that perhaps no one fully appreciated at the time, for the curriculum focused on mathematics, physics, chemistry, and the practical applications of scientific knowledge to engineering and industry. Where other boys of Paul's age and intellectual capacity might have been set to translating Virgil or parsing the syntax of Cicero, Paul instead found himself immersed in the quantitative and experimental subjects that would form the foundation of his later work. The Merchant Venturers Technical College had been established with the practical needs of Bristol's commercial and industrial enterprises firmly in mind, and its educational philosophy reflected the city's character as a center of manufacturing, shipping, and trade. The year 1914 brought changes that touched every corner of British life, including the classrooms of Bristol's schools. When the Great War began in August of that year, Paul was 12 years old and firmly established in his studies at the Merchant Venturers Technical College. Bristol, as an industrial city of considerable importance, found itself drawn into the national effort to supply the materials of war, and the factories that lined the riverbanks and filled the working districts shifted their production toward military necessities. The distant thunder of the conflict on the Western Front reached Bristol not as literal sound, of course, for the trenches of France and Flanders were far across the Channel, but rather as a constant presence in daily life, manifested in newspaper headlines, in the departure of young men for military service, in the gradual introduction of rationing as the German submarine campaign threatened Britain's food supplies, and in the general atmosphere of anxiety and sacrifice that characterized the home front during those long years of fighting. Paul was too young to serve, and so he continued his education while the war ground on, year after terrible year, claiming lives by the hundreds of thousands in battles whose names would become synonymous with horror and futility. The rationing of food meant that meals became plainer and portions more carefully measured, and families throughout Bristol learned to make do with less sugar, less meat, less of many things that had once been taken for granted. Within the walls of the Merchant Venturers Technical College, Paul's mathematical abilities began to manifest themselves with increasing clarity. His teacher in mathematics was a man named Mr. Pickering, who recognized in this quiet, reserved boy an unusual aptitude for numerical and logical reasoning. Under Mr. Pickering's instruction, Paul progressed through the mathematical curriculum with a speed and ease that set him apart from his classmates, demonstrating a facility for abstract thinking that seemed to require little effort on his part. The problems that other students found challenging Paul solved with a directness and economy that suggested he was perceiving something in the mathematics that others could not readily see. Mr. Pickering encouraged this ability, providing Paul with more advanced material and recognizing that here was a student whose talents deserved particular attention and cultivation. The relationship between a gifted teacher and an exceptional student is one of those quiet forces that shapes the course of individual lives and, through them, the broader currents of human knowledge, and in this case Mr. Pickering's guidance helped to set Paul on the path that would eventually lead him to the frontiers of theoretical physics. Paul's academic performance was sufficiently outstanding that he was permitted to skip 2 grades, advancing through the school at a pace well ahead of his age cohort. This acceleration meant that he moved through the curriculum rapidly, reaching the upper levels of the school while still quite young. His brother Felix was also enrolled at the Merchant Venturers Technical College, studying engineering, and so the two brothers found themselves in the same institution, following broadly similar technical courses of study. Felix, being older, was further along in his education, but the proximity meant that the brothers shared the experience of this practically oriented school and the particular educational philosophy it embodied. The relationship between Paul and Felix was complex, shaped by the dynamics of their family life and their quite different personalities, for Felix was more outgoing and socially comfortable while Paul remained withdrawn and solitary in his habits. Nevertheless, they proceeded through their studies in parallel, both absorbing the technical and scientific training that the Merchant Venturers Technical College provided. By 1918, as the Great War at last ground toward its conclusion with the exhaustion of Germany and the armistice signed in November, Paul had completed his secondary education at the remarkably young age of 16. His graduation from the Merchant Venturers Technical College marked the end of one phase of his education and the beginning of another, for the question now arose of what Paul should do next. Charles Dirac, with his emphasis on practical achievement and financial security, was insistent that his son should pursue a profession that would provide a stable and respectable living. The idea of studying pure mathematics or theoretical science, subjects without obvious commercial application, did not accord with Charles's vision of what constituted a proper education. Engineering, on the other hand, was eminently practical, a field that would equip Paul with skills directly applicable to industry and capable of securing him a reliable income. And so it was determined that Paul would enroll at Bristol University to study electrical engineering, following a path that seemed sensible and prudent, even if it did not entirely align with where Paul's deepest interests might naturally have led him. Bristol University in 1918 was a relatively young institution, having received its royal charter only 9 years earlier, though its roots extended back through earlier incarnations as a university college. Paul entered the engineering program and began his studies in electrical engineering, learning the principles of circuits, electromagnetism, and the practical applications of electrical science that were transforming industry and daily life in the early 20th century. The curriculum was demanding and technical, requiring students to master both theoretical principles and practical skills, to understand the mathematics underlying electrical phenomena and to apply that understanding to the design and construction of real systems. Paul approached these studies with his characteristic diligence, though the subject did not engage his imagination in the same way that pure mathematics had always done. He was competent, indeed more than competent, but engineering as a discipline did not stir in him the sense of intellectual excitement that he found in more abstract pursuits. During his time as an engineering student, Paul's abilities did not go unnoticed by the faculty of Bristol University. Two professors in particular, David Robertson and Peter Fraser, observed this quiet and reserved young man and recognized that his intellectual capacities extended beyond the ordinary run of engineering students. Robertson and Fraser saw in Paul a clarity of thought and a depth of understanding that marked him as someone of unusual promise, even if he rarely spoke in class and kept largely to himself. The academic environment of a university, with its opportunities for more advanced study and its exposure to a broader range of intellectual inquiry, began to open new horizons for Paul, even as he continued to pursue the practical engineering curriculum his father had prescribed. It was during these years of engineering study that Paul first encountered the work of Albert Einstein, and this encounter would prove to be one of the defining moments of his intellectual development. Einstein's theories of relativity, both the special theory published in 1905 and the general theory completed in 1915, were still relatively new and had not yet fully penetrated into the standard curriculum of most universities. But Paul, through his reading and through discussions within the university, came to learn of these revolutionary ideas about space, time, and the nature of physical reality. The elegance and profundity of Einstein's work captivated Paul in a way that engineering problems never had, revealing to him a realm of physical theory where mathematical beauty and deep truths about the universe were intimately connected. Here was physics pursued not merely as a practical enterprise for building machines and devices, but as a fundamental inquiry into the structure of reality itself, and Paul found himself drawn irresistibly toward this way of thinking. The discovery of Einstein's relativity theory planted a seed in Paul's mind, a recognition that the most profound questions about the physical world could be approached through the kind of mathematical reasoning that came so naturally to him. Paul's engineering studies also brought him into contact with applied mathematics courses that introduced him to Hamiltonian mechanics, a formulation of classical mechanics developed in the 19th century by the Irish mathematician William Rowan Hamilton. Hamiltonian mechanics provided a powerful and elegant framework for describing the motion of physical systems, using concepts such as generalized coordinates, momenta, and the Hamiltonian function to express the laws of motion in a form that revealed deep mathematical structures underlying physical phenomena. This first exposure to Hamiltonian mechanics would prove to be of enormous importance in Paul's later work, for the Hamiltonian formulation would become one of the essential tools he would use in developing his contributions to quantum mechanics. At the time, of course, Paul could not have known just how significant this knowledge would become, but the foundations were being laid, piece by piece, for the extraordinary achievements that lay ahead. Paul completed his engineering degree at Bristol University in 1921, having demonstrated throughout his studies the quiet brilliance that his professors had noted. He had even designed an electrical network as part of his coursework, showing a mastery of the practical skills that engineering demanded. With his degree in hand, it might have seemed that Charles Dirac's plan for his son had succeeded, that Paul was now equipped to enter the world of industry and secure the stable professional life his father had envisioned. But the world outside the university did not cooperate with these expectations. The years immediately following the Great War were a time of considerable economic difficulty in Britain, as the nation struggled to transition from a wartime to a peacetime economy and as the initial post-war boom gave way to a sharp recession. Jobs were scarce, businesses were failing, and young graduates found that the degrees they had worked so hard to earn did not guarantee employment. Paul, despite his abilities and his qualifications, could not find work as an engineer. He applied for positions, but the economic conditions of the time meant that opportunities simply did not exist in sufficient numbers to absorb all the young men and women emerging from the universities with their freshly minted degrees. This failure to find employment in engineering, which might have seemed at the time like a misfortune or a setback, proved instead to be one of those unexpected turns that alter the entire course of a life. Unable to pursue the practical career his father had intended for him, Paul was redirected toward other possibilities, and it was this redirection that would lead him away from engineering and toward the pure mathematics and theoretical physics where his true gifts would find their fullest expression. The post-war recession, with all its hardships and disappointments, had cleared a path that no one could have planned or predicted, a path that would lead Paul Dirac toward discoveries that would transform our understanding of the physical world. Paul Dirac had wanted to study at Cambridge from quite a young age, drawn to its mathematical reputation and the quiet promise of a life spent thinking carefully about the structure of things. But when he completed his electrical engineering degree at Bristol in 1921, at the age of just 19, his family simply could not afford to send him there. The scholarships he had won were not sufficient to cover the full costs of board and tuition at one of the ancient colleges, and so Cambridge remained, for the time being, a distant hope rather than an immediate destination. This is the sort of detail that often gets smoothed over in biographies, the practical matter of money, but it shaped the next 2 years of Dirac's life in ways that would prove unexpectedly fortunate. What happened instead was that the mathematics department at Bristol University offered him a place to study for a second degree, this time in mathematics rather than engineering, and they waived the fees entirely because of his obvious abilities. This was an unusual arrangement, a kind of informal scholarship born of necessity, and Dirac accepted it with his characteristic quietness. He had no particular attachment to engineering as a profession, having found the practical aspects of the subject rather less interesting than the theoretical foundations, and so the chance to spend 2 more years studying pure mathematics was genuinely welcome. He moved through the Bristol mathematics curriculum with the same unhurried thoroughness he had shown in engineering, attending lectures, working through problems, and beginning to develop the habits of solitary concentration that would define his working life. Those 2 years at Bristol, from 1921 to 1923, were in some ways a kind of apprenticeship in mathematical thinking. Dirac was exposed to more advanced techniques in calculus and algebra, to the methods of differential equations that would later prove essential in physics, and to the general style of rigorous argument that characterizes pure mathematics. He was not yet doing original research, but he was absorbing the tools he would need, storing them away in that remarkably retentive mind of his. The engineering training had given him a certain practical intuition about physical systems, a sense of how things actually behave in the world, and now the mathematical training was providing the formal language to describe such behavior with precision. The combination would prove extraordinarily powerful. By 1923, the situation had changed. Dirac had done well enough in his Bristol mathematics degree to win a studentship that would finally allow him to go to Cambridge, and in October of that year he arrived at St. John's College as a research student. The college is one of the larger foundations at Cambridge, with its long courts and chapel and the Bridge of Sighs spanning the River Cam, and Dirac was given rooms there in which to live and work. He was 21 years old, rather older than the typical undergraduate but still young for a research student, and he came to Cambridge knowing almost nothing about the revolutionary developments that were beginning to transform physics. His mathematical preparation was solid, but his physics was still largely that of the 19th century, the classical mechanics of Newton and the electromagnetism of Maxwell. He had much to learn, and fortunately he had been assigned to exactly the right supervisor to teach him. Ralph Fowler was a mathematical physicist of considerable reputation, a large and genial man who had done important work on statistical mechanics and thermodynamics. More significantly for Dirac's development, Fowler was one of the few people in Cambridge who was following closely the strange new ideas emerging from the continent, particularly from Niels Bohr's Institute in Copenhagen and from the German universities where young physicists were wrestling with the puzzles of atomic structure. Fowler introduced Dirac to Bohr's model of the atom, that curious picture in which electrons orbit the nucleus in discrete allowed paths, jumping between them in quantum leaps and emitting or absorbing light of specific frequencies as they do so. He introduced him to the older quantum theory more generally, that patchwork of rules and hypotheses that physicists had been developing since Max Planck's work on blackbody radiation at the turn of the century. It was all rather mysterious and not entirely self-consistent, but it worked surprisingly well for certain problems, and Fowler made sure that Dirac understood both its successes and its limitations. The intellectual atmosphere of Cambridge in those years was remarkable, though Dirac engaged with it only partially. The Cavendish Laboratory, where Ernest Rutherford presided over experimental investigations into the structure of matter, was just a short walk from St. John's College. Rutherford had discovered the atomic nucleus a decade earlier, and his laboratory was the World Center for Experimental Nuclear Physics, full of apparatus and activity and the particular energy that surrounds important scientific work. The legacy of earlier Cambridge figures hung over everything. The shade of Isaac Newton, who had been a Fellow of Trinity College just next door, and James Clerk Maxwell, who had established the Cavendish Laboratory itself in the 1870s and whose equations governing electromagnetism were among the most beautiful in all of physics. Dirac was aware of this heritage, certainly, but he did not seek out company or conversation in the way that some young scientists do. He preferred to work alone, to think things through in his own time, and to speak only when he had something definite to say. His daily routine at Cambridge became quite fixed, and he maintained its essential features for many years afterward. During the week he would work in his rooms or in the library, reading papers and working through calculations, occasionally attending lectures or meeting with Fowler. On Sundays, without fail, he would take a long solitary walk, sometimes for hours at a time, out into the flat countryside surrounding Cambridge. These walks were not merely exercise, though they served that purpose too. They were an essential part of his thinking process, a time when he would let his mind wander freely over whatever problem was currently occupying him, making connections and seeing possibilities that might not emerge during more focused work at his desk. The rhythm of walking, the absence of distraction, the gentle monotony of the fenland landscape, all of this seemed to help him think. He spoke to almost no one during these walks, and indeed he spoke to almost no one at any other time either. His social interactions were minimal, limited largely to the necessary exchanges with Fowler and a few other members of the Cambridge physics community. He ate his meals in college, often alone, and he is said to have sometimes become so absorbed in his work that he forgot to eat at all, missing meals entirely and emerging from his concentration only when physical hunger became impossible to ignore. In 1924, Dirac began to publish his first original research papers, short contributions on problems in statistical mechanics that Fowler had suggested to him. These early papers were competent and showed a clear mathematical style, but they were not yet the work of a revolutionary. Dirac was still learning, still absorbing the existing state of knowledge, still finding his way toward the problems that would matter most. He was quiet and patient, building his understanding piece by piece, and there was nothing in these early publications to suggest the extraordinary developments that would follow within just a year or two. Statistical mechanics is the branch of physics that connects the behavior of large numbers of particles to the thermodynamic properties of matter, things like temperature and pressure and entropy, and it requires considerable mathematical sophistication. Dirac's work in this area showed that he had mastered the relevant techniques, but it did not yet show the kind of deep originality that would later characterize his contributions to quantum theory. The pivotal moment came in September 1925, and it came through the mail. Ralph Fowler had received the proofs of a new paper by the young German physicist Werner Heisenberg, a paper that would turn out to be one of the founding documents of quantum mechanics. Heisenberg had taken a radical approach to the problems of atomic physics, abandoning any attempt to visualize what was happening inside atoms and focusing instead on the mathematical relationships between observable quantities. His paper introduced a new kind of algebra in which the order of multiplication mattered, so that multiplying A by B and then multiplying B by A would not necessarily give the same result. This was strange and unfamiliar mathematics for most physicists, and Heisenberg himself was not entirely sure what it meant. Fowler, recognizing that the paper was important but not quite knowing what to make of it, forwarded it to Dirac with a note asking for his opinion. Dirac read the paper and was initially puzzled. The mathematics was unusual, and the physical interpretation was unclear, and he set the paper aside for a time without making much progress. But then, during one of his Sunday walks, something shifted in his thinking. He was turning over in his mind the strange non-commutative multiplication that Heisenberg had introduced, the fact that A times B was not equal to B times A, and he began to wonder whether this peculiar feature might have a counterpart in classical mechanics. There was something familiar about it, some echo of a structure he had encountered before, but he could not quite place it. The walk ended without resolution, and he had to wait until the libraries opened on Monday morning to check his intuition. What he found was that the key lay in something called Poisson brackets, a mathematical device from classical mechanics that had been introduced by the French mathematician Siméon Denis Poisson in the early 19th century. Poisson brackets are a way of expressing the relationships between different physical quantities in classical mechanics, things like position and momentum, and they have a particular algebraic structure that mirrors, in a precise way, the non-commutative multiplication that Heisenberg had stumbled upon. Dirac realized that Heisenberg's quantum mechanics could be understood as a kind of generalization of classical mechanics, with the Poisson brackets of classical theory replaced by a new kind of bracket appropriate to the quantum world. This was a profound insight, a bridge between the old physics and the new, and it allowed Dirac to reformulate the entire mathematical structure of quantum mechanics in a clear and general way. Working with his usual intensity, sometimes forgetting meals entirely as the calculations absorbed him, Dirac developed these ideas into a complete paper over the following weeks. The paper was titled The Fundamental Equations of Quantum Mechanics, and it was submitted in November 1925, just 2 months after he had first seen Heisenberg's work. In it, Dirac established the mathematical framework of quantum algebra independently, showing how the new quantum theory could be derived from a few simple principles and how it connected to the classical mechanics that physicists already understood. The paper was remarkable for its clarity and generality, and it established Dirac immediately as one of the leading figures in the new quantum mechanics, despite his youth and relative obscurity. He was just 23 years old. The months that followed were extraordinarily productive. Dirac continued to develop his approach to quantum mechanics, exploring its implications and extending its mathematical structure. By May of 1926, he had completed his PhD thesis, titled simply Quantum Mechanics, which gathered together and refined the work he had done over the previous year. It was one of the first doctoral theses ever written on the new quantum theory, submitted at a time when the theory itself was barely a year old and still being actively constructed by a handful of physicists around the world. The thesis was examined and accepted, and Dirac was awarded his doctorate, becoming one of the very first people in history to hold such a qualification in this new branch of physics. The period from 1923 to 1926 had transformed Dirac from a promising but unknown student into one of the central figures of theoretical physics. He had arrived at Cambridge knowing little of quantum theory and left with a doctorate that helped to define the field. The combination of his Bristol training in both engineering and mathematics, his exposure to the new ideas through Fowler, his solitary habits of thought, and his particular gift for seeing mathematical structure beneath physical phenomena, all of these had come together in those years to produce something extraordinary. And yet Dirac himself remained much the same, quiet and solitary, taking his long Sunday walks, occasionally forgetting to eat, speaking only when he had something precise to say. The revolution he had helped to create was still in its early stages, and there was much more work to be done. In the autumn of 1926, Paul Dirac traveled from Cambridge to Copenhagen, where the great Niels Bohr had established his Institute for Theoretical Physics, and this journey marked the beginning of a period that would prove to be among the most productive in the entire history of physics, though of course Dirac himself would not have described it in such elevated terms, being as he was a man of few words and even fewer dramatic pronouncements. The Institute in Copenhagen had become something of a gathering place for the brightest young minds working on the new quantum theory, and Bohr, with his gentle manner and his endless capacity for conversation, had created an atmosphere of collaborative inquiry that attracted visitors from across Europe and beyond. Dirac arrived there in September, carrying with him his recent work on quantum mechanics and his characteristically reserved demeanor, and he soon found himself in the company of Werner Heisenberg and Wolfgang Pauli, two physicists whose contributions to the emerging theory were already substantial and whose personalities could not have been more different from his own. Heisenberg was energetic and intuitive, prone to leaps of insight that he would later justify with mathematics, while Pauli was sharp-tongued and critical, famous for his devastating assessments of work he considered inadequate. Dirac, by contrast, was quiet to the point of silence, speaking only when he had something precise to say and often responding to questions with answers of startling brevity. Bohr, who loved nothing more than long discussions that wound their way through philosophical tangles and physical puzzles, found Dirac's taciturnity somewhat bewildering, and he reportedly remarked that Dirac was the strangest man who ever visited Copenhagen, a comment that was not unkind but rather expressed a genuine puzzlement at this young Englishman who seemed to have no need for the social and intellectual discourse that Boe himself found so essential. There is a story, perhaps embellished in the retelling as such stories often are, that Boe once asked Dirac a question and received no reply for several minutes, after which Dirac finally spoke to explain that he was still considering whether the question required an answer at all. The atmosphere at Copenhagen was lively and informal, with physicists gathering for discussions that might begin over breakfast and continue well into the evening, interrupted only by walks along the harbor or games of table tennis at which Boe was enthusiastic if not particularly skilled. Dirac participated in these activities with a kind of detached willingness, present but not quite engaged in the way the others were, his mind apparently elsewhere even as his body occupied the same room. Yet this apparent disconnection was misleading, for Dirac was absorbing everything around him, turning over the ideas he encountered and fitting them into the mathematical structures that were taking shape in his thoughts. He attended the seminars and listened to the debates, and though he rarely contributed to the conversation in the moment, the influence of these exchanges would become apparent in the work he produced in the months that followed. By December of 1926, Dirac had completed a remarkable piece of work that he called transformation theory, and this contribution demonstrated his extraordinary ability to see through the apparent differences between competing approaches to find the deeper unity beneath. At that time, there existed two formulations of quantum mechanics that seemed quite distinct from one another. Erwin Schrödinger had developed his wave mechanics, which described quantum systems using continuous wave functions that evolved according to a differential equation, and this approach had an appealing familiarity to physicists trained in the classical tradition of waves and vibrations. Heisenberg, meanwhile, had constructed his matrix mechanics, which represented physical quantities as arrays of numbers that obeyed certain algebraic rules, and this approach was more abstract, less easily visualized, but powerfully effective in its calculations. The two methods gave the same answers when applied to the same problems, yet they appeared to rest on fundamentally different mathematical foundations, and physicists were uncertain whether one was more correct than the other or whether both were merely approximate descriptions of some deeper reality. Dirac's transformation theory resolved this puzzle by showing that wave mechanics and matrix mechanics were not two different theories at all but rather two different representations of a single underlying mathematical structure. He introduced a general framework in which quantum states could be expressed in various ways, with Schrödinger's wave functions and Heisenberg's matrices emerging as special cases corresponding to particular choices of representation. The mathematics involved was elegant and powerful, drawing on techniques that Dirac developed or adapted for the purpose, and the result was a unified formulation of quantum mechanics that revealed the essential features of the theory while stripping away the accidents of any particular approach. This work established Dirac as one of the leading figures in quantum physics, not merely a contributor to the field but one of its architects, and it demonstrated a style of thinking that would characterize all his subsequent contributions: the relentless pursuit of mathematical beauty as a guide to physical truth. In February of 1927, Dirac published another paper that opened an entirely new chapter in theoretical physics, a chapter that we now call quantum electrodynamics. The problem he addressed was the interaction between matter and the electromagnetic field, a topic that had occupied physicists since the earliest days of the quantum theory but had never been treated in a fully satisfactory way. Einstein had shown in 1905 that light could behave as though it were composed of discrete particles, later called photons, and this insight had been essential to understanding phenomena such as the photoelectric effect, but no one had yet succeeded in constructing a complete quantum mechanical description of the electromagnetic field itself. Dirac's paper provided the first such description, treating the field not as a classical entity that happened to emit and absorb photons but as a genuinely quantum system with its own states and its own dynamics. The mathematical tools he introduced in this paper were creation and annihilation operators, which allowed him to describe the appearance and disappearance of photons in a precise and systematic way. A creation operator, when applied to a quantum state, produces a new state containing one additional photon, while an annihilation operator removes a photon from the state, and these operations obey certain algebraic relations that encode the fundamental properties of photons, including the fact that they are indistinguishable from one another and can occupy the same quantum state in unlimited numbers. With these operators, Dirac could calculate the probabilities for various processes involving light and matter, such as the emission and absorption of photons by atoms, and his results agreed with the earlier formulas that had been derived through more ad hoc methods while placing them on a rigorous theoretical foundation. This paper marked the beginning of quantum field theory, a framework that would eventually grow to encompass not only electromagnetism but all the fundamental forces of nature, and though Dirac himself did not foresee all these developments, he had opened a door through which generations of physicists would pass. In 1927, Dirac was elected to a fellowship at St. John's College in Cambridge, a recognition of his achievements that provided him with the security and the freedom to continue his research without distraction. The life of a Cambridge Fellow suited him well, with its quiet routines and its tolerance for eccentricity, and Dirac settled into a pattern of work that he would maintain for many years, spending his mornings on physics, his afternoons on long solitary walks through the countryside, and his evenings on reading or quiet reflection. He also traveled during this period, visiting Göttingen in Germany, where he met Max Born and Pascual Jordan, two physicists who had collaborated with Heisenberg on the development of matrix mechanics, and where he encountered the young Robert Oppenheimer, an American who was then completing his doctoral studies and who would later become famous for quite different reasons. These meetings were cordial if not effusive, for Dirac was never one to form close friendships quickly, but they kept him connected to the wider community of physicists who were collectively building the new quantum theory. In the latter part of 1927, Dirac turned his attention to a problem that had been troubling him and others for some time, the question of how to combine quantum mechanics with Einstein's special theory of relativity. The quantum mechanics that existed at that time was not relativistic, meaning that it did not incorporate the principles of special relativity, and this was a significant limitation. For the electrons in atoms can move at speeds that are a substantial fraction of the speed of light, fast enough that relativistic effects become important. Schrödinger had attempted to write a relativistic wave equation early in his work, but had set it aside because it gave incorrect predictions for the hydrogen atom, and others had tried various approaches without success. The difficulty was not merely technical but seemed to involve something deep about the structure of quantum theory, and many physicists believed that a fully relativistic quantum mechanics might require entirely new concepts or even a radical revision of the foundations. Dirac approached this problem in his characteristic way, seeking not a clever trick or a computational shortcut but a mathematically beautiful equation that would naturally incorporate both quantum mechanics and special relativity. He worked on this through the autumn of 1927, trying various forms and testing them against the known properties of electrons, and for a time he made little progress, the equations either failing to satisfy the requirements of relativity or giving results that contradicted experiment. Then, in December of that year and continuing into January of 1928, he had his breakthrough. The equation he found was simple in its structure yet profound in its implications, and it emerged from his insistence on a particular form of mathematical elegance rather than from any physical intuition about what electrons ought to do. Years later, when asked about this discovery, Dirac said that he was not trying to get a theory of the electron but was trying to get a beautiful equation, and this remark captures something essential about his approach to physics, the belief that mathematical beauty is not merely a pleasant bonus but a reliable guide to truth. The Dirac equation, as it came to be called, takes a form that can be written compactly using the notation of modern physics. In symbols, it reads I gamma mu partial mu minus m, all multiplied by the wave function psi, equals 0. This compact expression encodes a great deal of physics, and to unpack it fully would require a lengthy discussion of the mathematical objects involved, but for our present purposes it is enough to note that the equation describes how the quantum state of an electron evolves in space and time, subject to the constraints imposed by special relativity. The gamma symbols with their subscript mu are matrices, for by four arrays of numbers that satisfy certain algebraic relations, and their presence in the equation is what gives it its distinctive character and its remarkable predictive power. Dirac published his equation in 2 papers in February of 1928, and the physics community quickly recognized that something extraordinary had been achieved. The equation automatically predicted that electrons possess a property called spin, an intrinsic angular momentum that had been discovered experimentally a few years earlier but had been added to quantum mechanics by hand, without any deeper justification. In Dirac's equation, spin emerged naturally, as an inevitable consequence of the mathematical structure, requiring no additional assumptions or adjustable parameters. Furthermore, the equation gave the correct value for the magnetic moment of the electron, a quantity that measures how strongly the electron interacts with magnetic fields, and this too had previously been fitted to experiment rather than derived from first principles. These successes were remarkable, suggesting that Dirac had found not merely a useful approximation but something close to the true description of the electron. Yet the equation also contained puzzles, aspects that were not so easily interpreted and that would occupy physicists for years to come. Among these were the negative energy solutions, mathematical possibilities allowed by the equation that seemed to have no physical meaning. In the classical physics of Newton and even in the non-relativistic quantum mechanics of Schrödinger, The energy of a particle is always positive or at worst zero, corresponding to a particle at rest. But the Dirac equation admitted solutions with negative energy, states in which an electron would have less energy than nothing at all, and this was deeply troubling, for it suggested that ordinary electrons should be able to fall into these negative energy states, releasing energy as they did so, a process that would make all matter unstable. Dirac did not immediately resolve this puzzle, and for a time the negative energy solutions remained an awkward feature of an otherwise beautiful theory, a shadow cast by the equation's mathematical perfection. The story of how Dirac eventually interpreted these solutions, proposing the existence of a new particle that we now call the positron, belongs to a later section of this narrative, and we shall come to it in due course. For now, it is enough to rest with the equation itself, written down in early 1928 by a young man in Cambridge who sought beauty and found, along with it, a deeper understanding of the electron than anyone had thought possible. The Dirac equation remains one of the central achievements of 20th century physics, a monument to the power of mathematical reasoning guided by aesthetic principles, and it continues to be studied and used by physicists today, nearly a century after its discovery. In the quiet of a Cambridge college, working alone with his pencil and paper, Paul Dirac had changed our understanding of the physical world, and he had done so by following the mathematics wherever it led, trusting that beauty and truth were, in the end, the same thing. In the years following 1928, when Paul Dirac had set down his remarkable equation describing the electron, there emerged from the mathematics a peculiar and rather troubling feature that would occupy his thoughts for some time to come. The equation, you see, was wonderfully successful in many respects, accounting for the electron's spin and its magnetic properties in a way that felt natural and inevitable rather than imposed from without. Yet buried within its elegant structure lay solutions that seemed, at first glance, to make no physical sense whatsoever, and it is these strange solutions, and the journey Dirac undertook to understand them, that we shall gently explore as you settle in and let your breathing slow. The difficulty centered on what physicists call negative energy states. When one solved the Dirac equation for the possible energies an electron might possess, half of the solutions corresponded to positive energies, which was perfectly reasonable and expected, while the other half corresponded to negative energies, which was deeply perplexing. In classical physics, and in earlier quantum mechanics, one could simply declare that negative energy states were unphysical and ignore them, much as one might dismiss a negative solution for the length of a piece of string. But the Dirac equation was different, constructed in such a way that these negative energy solutions could not be so easily set aside. They were woven into the very fabric of the theory, appearing with just as much mathematical legitimacy as their positive counterparts, and moreover, the principles of quantum mechanics seemed to demand that an electron in a positive energy state should be able to transition down into these negative energy states, releasing energy as it fell, and then continue falling forever into ever more negative energies. This would be catastrophic, as all the electrons in the universe would cascade downward without limit, radiating infinite amounts of energy in the process. Clearly something was wrong with this picture, or rather, something was incomplete in the understanding of what these solutions might mean. Dirac thought about this problem carefully, as was his nature, and by December of 1929 and into 1930, he had arrived at a radical and imaginative proposal that would come to be known as his whole theory. Rather than dismissing the negative energy states, Dirac suggested that they were all already occupied. He pictured the vacuum itself, what we might think of as empty space, as being filled completely with electrons in all the negative energy states, a vast and infinite sea of particles extending down to arbitrarily low energies. This sea would normally be undetectable, forming a kind of background against which ordinary physics would unfold, precisely because every negative energy state was already filled and there was nowhere for positive energy electrons to fall to. The exclusion principle that Wolfgang Pauli had articulated a few years earlier, which states that no two electrons can occupy the same quantum state, would prevent any additional electrons from joining the sea, and so the catastrophic cascade would be avoided. But here is where the proposal became truly interesting, and where Dirac's physical intuition led him toward something entirely new. If the vacuum was this filled sea of negative energy electrons, then what would happen if one of those electrons were somehow removed, lifted up into a positive energy state by the absorption of sufficient energy? The sea would then have a hole in it, an absence where an electron ought to be. Dirac reasoned that this hole, this missing negative energy electron, would appear to observers as something quite peculiar, a particle with positive energy, since the absence of negative energy is equivalent to the presence of positive energy, and a particle with positive charge, since the absence of a negative charge is equivalent to the presence of a positive charge. The whole would behave, in every observable respect, as a new kind of particle, one with properties opposite to those of the electron in certain key ways. Initially, Dirac was cautious about what this whole might represent, and in his first explorations of the idea he speculated that perhaps the holes were protons. This seemed appealing in some ways, as it would mean that the only fundamental particles needed were electrons and protons, with protons emerging naturally from the sea of negative energy electrons rather than being an entirely separate kind of matter. However, there was an immediate and rather serious difficulty with this identification. Protons are nearly 2,000 times more massive than electrons, and there seemed to be no good reason within the theory why a hole should have a different mass from the electron whose absence it represented. The mathematics of the whole theory suggested that holes and electrons should have the same mass, which ruled out the proton interpretation, though Dirac initially hoped that some mechanism might be found to explain the mass difference. By 1931, Dirac had accepted that the whole could not be a proton and that his theory was predicting something altogether more radical, the existence of an entirely new particle that had never been observed. In a paper published that year with the title Quantized Singularities in the Electromagnetic Field, Dirac described what he called an anti-electron, a particle with the same mass as the ordinary electron but carrying a positive charge rather than a negative one. This was the first clear prediction of what we now call antimatter, a mirror version of ordinary matter with reversed electrical properties, and it emerged not from experimental observation but purely from the internal logic of a mathematical theory combined with a willingness to take strange solutions seriously. The same paper contained another speculation that was perhaps even more daring, though it would not receive experimental confirmation in Dirac's lifetime. He considered whether magnetic monopoles might exist, isolated north or south magnetic poles without their usual partner. In everyday experience, magnets always have both a north pole and a south pole, and if one cuts a magnet in half, one does not obtain a separate north piece and south piece but rather two smaller magnets, each with its own north and south poles. Dirac showed that the existence of magnetic monopoles would not contradict any fundamental principle of physics and would in fact provide an elegant explanation for why electric charge appears to come in discrete units, a deep question that had no other satisfying answer. The magnetic monopole remains hypothetical to this day, searched for in cosmic rays and accelerator experiments without definitive success, but Dirac's analysis of its theoretical properties continues to influence how physicists think about fundamental symmetries. The anti-electron that Dirac had predicted was detected experimentally just a year later, in August of 1932, by a young physicist named Carl Anderson working at the California Institute of Technology. Anderson was studying cosmic rays, those high-energy particles that rain down upon the Earth from outer space, using a device called a cloud chamber placed within a strong magnetic field. The cloud chamber made visible the paths of charged particles as trails of tiny droplets, much like the contrails left by high-flying aeroplanes, and the magnetic field caused the paths to curve, with the direction of the curve revealing whether the particle carried positive or negative charge and the tightness of the curve indicating the particle's momentum and mass. Among the many tracks Anderson photographed, some appeared to be caused by particles with the mass of an electron but curving in the wrong direction, indicating a positive rather than negative charge. These were positrons, though Anderson did not initially call them by that name, and their existence matched precisely what Dirac had predicted from his whole theory. Further confirmation came the following year from Patrick Blackett and Giuseppe Occhialini working at the Cavendish Laboratory in Cambridge, who observed positrons being created in pairs with electrons when high-energy gamma rays interacted with matter. This pair production, as it came to be called, was exactly what the whole theory described, the gamma ray providing enough energy to lift a negative energy electron out of the sea and into a positive energy state, leaving behind a hole that appeared as a positron. The experimental and theoretical pictures were aligning beautifully, and the scientific community recognized that something profound had been achieved, a genuinely new form of matter predicted from pure theory and then found in nature. In November of 1933, the Nobel Prize in Physics was awarded jointly to Paul Dirac and Erwin Schrödinger for the discovery of new productive forms of atomic theory. Dirac was just 31 years old at the time, making him one of the youngest recipients of the prize in its history, and the recognition came remarkably swiftly after his major theoretical contributions, reflecting how clearly the importance of his work was understood by his contemporaries. Schrödinger, who was 11 years older, had developed his own version of quantum mechanics, the wave equation approach, which was different in formulation from Dirac's but equivalent in its physical content, and together their work had provided the foundation for modern atomic and subatomic physics. There is a gentle anecdote concerning Dirac's reaction to the news that he had been selected for this honor. His natural inclination was to refuse the prize, not from any lack of appreciation for the recognition but simply because he found the prospect of publicity and public attention thoroughly unpleasant. Dirac was a private man who preferred equations to conversations and who found social obligations draining rather than rewarding. Ernest Rutherford, The director of the Cavendish Laboratory and a Nobel laureate himself, learned of Dirac's intentions and advised him against refusal. Rutherford pointed out, quite sensibly, that declining the Nobel Prize would attract far more attention and publicity than simply accepting it quietly and getting on with one's work. Dirac, recognizing the practical wisdom in this advice, accepted the prize after all. The Nobel ceremony took place in Stockholm in December of that year, and Dirac's mother Florence made the journey to Sweden to witness her son receive the medal and diploma from the Swedish king. One can imagine her quiet pride, having supported her son through his schooling and encouraged his studies, now seeing him honored by the scientific world for achievements she could perhaps not fully follow in their technical details but could certainly appreciate in their significance. Dirac's father Charles did not attend the ceremony, and indeed the relationship between father and son had always been distant and difficult, marked by the peculiar household routines of Dirac's childhood and the isolation those routines imposed. Charles Dirac passed away in 1936, 3 years after the Nobel Prize was awarded, and Paul attended the funeral but is said to have shown little outward emotion, though the inner landscape of his feelings toward his father remained, as with so many of his personal matters, largely unspoken. On the 12th of December 1933, Dirac delivered his Nobel lecture, titled Theory of Electrons and Positrons, in which he set out the ideas of his whole theory and the prediction of antimatter for the assembled audience. The lecture was characteristically clear and methodical, presenting the logic that had led from the puzzling negative energy solutions through to the hypothesis of the filled sea and onward to the prediction and discovery of the positron. He also looked forward, speculating about whether there might exist antiprotons, the antimatter counterparts of protons, which would be holes in a hypothetical sea of negative energy protons. Such particles would indeed be discovered more than 2 decades later, in 1955, extending the antimatter concept beyond electrons just as Dirac had foreseen. And so by the end of 1933, Paul Dirac had achieved a kind of completeness in his early theoretical work, having built his equation, faced its strange implications honestly, proposed a bold interpretation, seen that interpretation vindicated by experiment, and received the highest recognition his field could offer. The positron was real, antimatter was real, and the vacuum itself was revealed to be not emptiness but something richer and more dynamic, a sea from which new particles could be drawn given sufficient energy. These ideas would evolve and be reformulated in the years to come, eventually giving way to the more sophisticated framework of quantum field theory, but the essential insight remained, that for every particle there exists an antiparticle, a shadow twin with reversed properties, and that this doubling emerges inevitably from the marriage of quantum mechanics and special relativity that Dirac first achieved. You may let these thoughts drift now, the sea of electrons, the holes that appear as positrons, the quiet journey from mathematical puzzle to experimental fact, all settling gently into the background as you breathe slowly and rest. In the autumn of 1932, Paul Adrien Maurice Dirac was elected to the Lucasian Professorship of Mathematics at the University of Cambridge, a position of considerable historical weight and scholarly distinction, one that had been held centuries earlier by Isaac Newton himself, and which would later pass to Charles Babbage, the pioneer of mechanical computation, and much later still to Stephen Hawking, whose name would become synonymous with cosmology and black holes in the popular imagination. Dirac was 29 years old at the time of his election, making him one of the youngest individuals ever to occupy this venerable chair, though by that point in his career he had already accomplished work of such profound importance that his youth seemed almost incidental to those who understood the magnitude of his contributions. The Lucasian professorship carried with it no requirement for extensive teaching, which suited Dirac's temperament admirably, for he was a man who preferred the quiet contemplation of mathematical structures to the bustle of large lecture halls and the social obligations that came with more administratively demanding positions. Cambridge would remain his intellectual home for decades to come, and the rooms and corridors of St. John's College, along with the broader university environment, provided him with the steady, unvarying conditions he seemed to require for his deepest thinking. 2 years before his election to the Lucasian chair, in 1930, Dirac had published a textbook that would shape the education of physicists for generations, a work entitled The Principles of Quantum Mechanics, which presented the new physics in a manner quite unlike anything that had come before. Where other textbooks of the period approached quantum mechanics through the historical development of the subject, tracing the path from classical physics through the various paradoxes and experimental puzzles that had led to the quantum revolution, Dirac chose instead to begin from abstract mathematical foundations, building the theory from a small number of clearly stated principles and deriving consequences through rigorous logical development. The book was not easy reading, for Dirac made few concessions to readers who might prefer intuitive physical pictures over formal mathematical structures, but for those who persevered, it offered a view of quantum mechanics that was remarkably clean and unified. One of the most distinctive features of the book, and one that would prove enormously influential, was Dirac's introduction of a new notation for describing quantum states and the mathematical operations performed upon them, a system that came to be known as bracket notation after the symbols he employed. In this notation, a quantum state is written as a ket, which looks rather like a vertical line followed by a label and enclosed in an angled bracket, while the corresponding dual state, which one uses when calculating probabilities and expectation values, is written as a bra, resembling an angled bracket enclosing a label followed by a vertical line. When a bra and a ket are combined, the result is a bracket, and this simple visual pun gave the notation its name. The elegance of this system lay in its ability to express complex quantum mechanical relationships in a compact and manipulable form, freeing physicists from the clumsier matrix and wave function formalisms that had previously dominated, and allowing them to focus on the essential logical structure of the theory rather than the accidents of any particular representation. The Principles of Quantum Mechanics went through multiple editions over the following decades, with Dirac carefully revising and expanding the text to incorporate new developments while maintaining the austere clarity that characterized his approach. Generations of physics students would come to regard the book with a mixture of reverence and trepidation, for while it was universally acknowledged as a masterpiece of scientific exposition, it demanded from its readers a willingness to follow long chains of abstract reasoning without the comfort of familiar physical analogies. Those who mastered its contents, however, emerged with a profound understanding of quantum mechanics that served them well throughout their careers, and many of the leading physicists of the 20th century would later credit Dirac's textbook with shaping their understanding of the subject at a formative stage. Throughout the 1930s, Dirac continued to work on problems in quantum field theory, the extension of quantum mechanics to systems with infinitely many degrees of freedom, such as the electromagnetic field and other fields that pervade all of space. One of his notable contributions during this period was the development, in collaboration with the Soviet physicist Vladimir Fock and the American Boris Podolsky, of what became known as the multi-time formalism, an approach that sought to place quantum field theory on a more relativistically covariant foundation. The difficulty that motivated this work was a subtle one, having to do with the way time enters into the equations of quantum mechanics. In ordinary quantum mechanics, time is a parameter that labels the evolution of a system, and all particles in a system share a common time coordinate. But in special relativity, the notion of simultaneity is observer-dependent, and different observers moving relative to one another will disagree about which events are simultaneous. This creates a tension when one tries to combine quantum mechanics with relativity, for the single universal time of quantum mechanics does not sit comfortably with the many possible time coordinates of relativistic physics. The Dirac-Fock-Podolsky formalism addressed this by introducing a separate time variable for each particle in a system, allowing the quantum state to depend on all these times independently, and showing that the resulting equations transformed correctly under the Lorentz transformations of special relativity. The formalism was mathematically elegant and helped clarify certain conceptual issues, though it did not by itself solve the deeper problems that plagued quantum field theory. In 1933, Dirac published a paper that would not reveal its full significance until more than a decade later, when a young American physicist named Richard Feynman would develop it into one of the most powerful tools in theoretical physics. The paper concerned the role of the Lagrangian in quantum mechanics, and it explored how one might reformulate quantum theory using concepts borrowed from classical mechanics. In classical physics, the Lagrangian is a function that encodes the dynamics of a system, and the principle of least action states that the actual path taken by a particle between 2 points is the one that makes a certain integral of the Lagrangian stationary. Dirac showed that analogous ideas could be brought into quantum mechanics, and he derived a connection between the quantum mechanical propagator, which describes how probability amplitudes evolve from one configuration to another, and exponentials involving the classical Lagrangian integrated along paths. The paper was characteristically concise and somewhat cryptic, and it did not immediately attract widespread attention, but when Feynman encountered it in the early 1940s, he recognized its potential and developed from it the path integral formulation of quantum mechanics, in which quantum amplitudes are computed by summing over all possible paths a particle might take, each path weighted by a phase factor involving the classical action. This reformulation proved extraordinarily fruitful, particularly in the context of quantum field theory, where path integrals provided a natural and flexible framework for calculations that had previously been cumbersome or intractable. While Dirac's professional life proceeded along its quiet and productive course, his personal life underwent a significant transformation in the mid-1930s, when he met and eventually married Margit Wiener, a Hungarian woman who was the sister of the physicist Eugene Wiener. Margit, who was known to her friends and family as Manci, had been born Margit Borlash in Budapest, and she had previously been married and divorced, with 2 children from her first marriage, a daughter named Judith and a son named Gabriel. The circumstances of their meeting were characteristic of Dirac's social reticence and the important role that scientific colleagues often played in connecting him to the wider world. Eugene Wiener, who had known Dirac through their overlapping work in physics, introduced his sister to his taciturn colleague, perhaps recognizing that despite Dirac's formidable reserve, there might be compatibility between them. The introduction occurred, and Dirac, true to form, said almost nothing during their initial encounter, offering little of the conversation that might be expected in such circumstances. Yet despite his silence, or perhaps in some way because of it, he was smitten, and the connection that formed between them proved lasting. The courtship was unconventional by ordinary standards, for Dirac was not a man given to romantic gestures or easy expressions of feeling, but Mansi possessed a warmth and persistence that gradually drew him out, and she came to understand that his silences did not signify indifference but rather a different mode of being in the world. They were married on the 2nd of January, 1937, in London, and Dirac adopted Mansi's 2 children, Judith and Gabriel, giving them his name and accepting responsibility for their upbringing. The family settled at No. 7 Cavendish Avenue in Cambridge, a house that would be their home for many years, and which provided the domestic stability within which Dirac could continue his work. Mansi brought a liveliness to their household that contrasted with Dirac's reserve, and she managed the social obligations and practical affairs that he found so difficult, creating a space in which his peculiar genius could flourish. In 1940, their daughter Mary Elizabeth was born, and 2 years later, in 1942, a second daughter, Florence Monica, arrived, completing the family. The Dirac household was by all accounts a happy one, with Mansi providing the emotional warmth and social competence that Dirac himself lacked, and with Dirac offering in return a steady devotion that, while not expressed in conventional ways, was nonetheless deeply felt. As the 1930s drew toward their close, Dirac's attention remained focused on the problems of quantum field theory, and he became increasingly troubled by the appearance of infinities in the calculations of quantum electrodynamics, the quantum theory of electrons and photons interacting via electromagnetic forces. When physicists attempted to calculate quantities such as the self-energy of the electron, they found that the integrals diverged, yielding infinite results that clearly could not correspond to physical reality. Various approaches to this problem were proposed over the years, and by the late 1940s, a procedure known as renormalization had been developed, principally by Feynman, Julian Schwinger, and Shinichiro Tominaga, which allowed physicists to extract finite, physically meaningful predictions from the divergent expressions. The technique involved carefully subtracting infinite quantities in a consistent manner, absorbing the infinities into redefinitions of the physical parameters of the theory, such as mass and charge. The predictions that emerged from this procedure were extraordinarily accurate, agreeing with experimental measurements to many decimal places, and renormalization became a standard tool in theoretical physics. Dirac, however, never accepted renormalization as a satisfactory solution. To him, the appearance of infinities signaled a fundamental flaw in the theory, a sign that quantum electrodynamics, despite its empirical successes, was not the final word. The procedure of subtracting infinities struck him as a mathematical sleight of hand rather than a principled derivation, and he believed that a truly correct theory would not require such maneuvers. This conviction was connected to a deeper philosophical commitment that guided much of Dirac's thinking, namely the belief that mathematical beauty was a reliable guide to physical truth. Throughout his career, Dirac had been drawn to equations and formulations that possessed an aesthetic elegance, a quality of simplicity and inevitability that he felt marked them as correct. He had found this beauty in the Dirac equation, with its natural incorporation of spin and its prediction of antimatter, and he expected that the ultimate theory of quantum electrodynamics, when it was finally discovered, would exhibit a similar elegance rather than the awkward infinities and ad hoc subtractions of the renormalized theory. This insistence on mathematical beauty was not merely a personal preference but a methodological principle, and Dirac argued for it explicitly in lectures and writings, suggesting that physicists should trust beautiful equations even when experimental confirmation was not immediately available, for nature, he believed, was fundamentally mathematical in its structure, and the deepest truths would inevitably possess mathematical beauty. In September of 1939, the familiar rhythms of Cambridge began to shift in ways both subtle and profound, as news of war spread through the ancient colleges and along the quiet pathways beside the River Cam. The declarations came through wireless sets and in the careful columns of newspapers, and Paul Dirac, now 37 years old and well established as one of the most distinguished theoretical physicists of his generation, found himself watching the transformation of a place he had come to know intimately over nearly 2 decades. The younger students began to disappear, called away to training camps and military service, and the lecture halls that had once held eager audiences for discussions of quantum mechanics and mathematical physics grew noticeably emptier, though never entirely silent. Cambridge itself took on the quiet vigilance of a nation preparing for uncertain years ahead, with blackout curtains appearing in college windows and the occasional distant drone of aircraft passing overhead on their way to or from the Channel. Dirac continued his teaching duties throughout these years, delivering lectures to the reduced numbers of students who remained, many of them studying accelerated courses or engaged in specialized training that the war effort required. His manner in the classroom had always been methodical and unhurried, proceeding through derivations with careful precision, and this quality seemed particularly well suited to the strange atmosphere of wartime study, when the normal academic calendar had been compressed and rearranged to meet the demands of the moment. He would stand at the blackboard, chalk in hand, working through the mathematics of quantum field theory or the properties of the electron with the same steady attention he had always brought to such matters, as though the elegant structures of theoretical physics existed in a realm somewhat apart from the turbulence of world events, which in a certain sense they did. Yet Dirac was not entirely removed from the practical concerns of the war, for his expertise in mathematical physics made him valuable to those working on the most secret and consequential scientific project of the era, the effort to develop an atomic bomb before Germany could achieve the same goal. The British program, which would come to be known by the deliberately obscure name tube alloys, brought together many of the finest physicists in the country, and Dirac was consulted on certain theoretical aspects of the work, particularly those related to the separation of uranium isotopes. The challenge facing the project was considerable, as natural uranium contains only a small fraction of the fissile isotope uranium-235, mixed with the far more abundant uranium-238, and separating these two nearly identical atoms in sufficient quantities to produce a weapon required methods of extraordinary delicacy and scale. One approach to this separation involved the use of gas centrifuges, spinning cylinders in which uranium hexafluoride gas would be subjected to tremendous centrifugal forces, causing the slightly heavier molecules containing uranium-238 to migrate outward while the lighter molecules containing uranium-235 concentrated toward the center. Dirac turned his attention to the mathematics of this process, applying his characteristic rigor to the statistical behavior of molecules in a centrifuge and to the question of how multiple centrifuges might be arranged in cascading sequences to achieve ever greater degrees of enrichment. His work on cascade theory contributed to the understanding of how such systems could be designed and optimized, though the practical engineering challenges remained formidable, and the actual construction of centrifuge facilities would prove to be one of the most demanding technical undertakings of the war. In the course of this theoretical work, Dirac made a suggestion that was entirely typical of his approach to physics, elegant in its conception and somewhat impractical in its execution. He proposed the possibility of using a very long single-stage centrifuge, extended to such a length that the separation could be achieved in one continuous process rather than through the repeated cycling of material through multiple shorter centrifuges. The idea had a certain mathematical beauty to it, eliminating the inefficiencies inherent in transferring gas between stages and allowing the enrichment to proceed in a single smooth gradient along the length of the device. Those who considered the proposal recognized its theoretical appeal while also recognizing the considerable engineering difficulties that would attend the construction of such an apparatus, which would need to maintain precise tolerances and high rotational speeds across an impractical length. The suggestion remained in the realm of interesting ideas rather than practical implementation, a characteristic outcome for many of Dirac's ventures into applied problems, where his instinct was always toward the mathematically pure solution rather than the merely workable one. His correspondence during this period included exchanges with Rudolf Peierls, the German-born physicist who had fled to Britain and who, together with Otto Frisch, had written the famous memorandum calculating that an atomic bomb could be built with a surprisingly small amount of fissile material. Dirac also maintained contact with James Chadwick, the discoverer of the neutron, who played a central role in the British atomic effort and who would later join the Manhattan Project in America as the head of the British mission. These letters were necessarily circumspect, given the classified nature of the work, but they connected Dirac to the larger community of physicists who were grappling with both the technical challenges and the profound moral implications of what they were attempting to create. Unlike many of his colleagues, Dirac declined the invitation to relocate to Los Alamos, the secret laboratory in the New Mexico desert where the American atomic bomb project was concentrated. Several British physicists made the journey across the Atlantic to contribute their expertise to this massive undertaking, working alongside American colleagues in the isolated community that J. Robert Oppenheimer had assembled among the mesas and pine forests of the Pajarito Plateau. Dirac preferred to remain in Cambridge, continuing his theoretical consulting work from a distance and maintaining the routines of academic life that he had established over many years. The reasons for this choice were likely multiple. encompassing his natural inclination toward solitude and familiar surroundings, his preference for the contemplative pace of Cambridge over the intense collaborative atmosphere of a weapons laboratory, and perhaps also a certain ambivalence about the enterprise itself, a reluctance to immerse himself fully in work whose ultimate purpose was the destruction of cities and the killing of enormous numbers of people. This ambivalence about atomic weapons would become more apparent in the years following the war, when the full consequences of the Manhattan Project were revealed to the world in the devastation of Hiroshima and Nagasaki. Dirac never became as vocal in his opposition to nuclear weapons as some of his colleagues, but neither did he express enthusiasm for the achievement or pride in his contribution to it. His relationship to the atomic project remained somewhat detached, that of a mathematician who had solved certain interesting problems rather than a committed participant in a great national effort. Some physicists threw themselves into the work with patriotic fervor or with the conviction that defeating fascism justified any means necessary, while others, like Dirac, contributed their expertise while maintaining a certain emotional and moral distance from the ultimate purpose of that expertise. Throughout these years of war, Dirac's personal life continued in the modest house on Cavendish Avenue where he lived with Margit and their two young daughters, Mary and Monica. Wartime rationing meant careful management of food and household supplies, and Margit took on the primary responsibility for navigating these domestic challenges, ensuring that the family remained comfortable despite the shortages and restrictions that affected everyone in Britain. She managed the household with practical efficiency, allowing Dirac to maintain his focus on his theoretical work and his consulting duties, a division of labor that suited his temperament and capabilities. He was not skilled at the ordinary tasks of domestic life and showed little interest in developing such skills, leaving to Margit the countless small decisions and arrangements that keep a household functioning. As a father, Dirac struggled with the emotional intimacy that young children naturally seek from their parents. He loved his daughters in his way, but the expression of that love did not come easily to a man who had always found human connection difficult and who had grown up in a household where warmth and spontaneity were suppressed by his father's rigid control. He showed affection through the means available to him, taking his daughters on walks through the Cambridge countryside, where his lifelong love of nature could be shared without the need for extensive conversation, and engaging them in simple problems and puzzles that reflected his mathematical turn of mind. These interactions were genuine expressions of care, even if they lacked the easy warmth that other fathers might provide. The girls grew up knowing that their father was an unusual man, brilliant and kind in his fashion but remote in ways that could be difficult for children to understand. During this period, Dirac may have found himself reflecting on his own childhood and on the brother he had lost many years before. Felix Dirac had taken his own life on the 20th of March, 1925, when Paul was still a young researcher just beginning to make his mark in physics. The suicide had occurred during a period of intense creative work for Dirac, and he had processed the loss in his characteristically private way, continuing with his research and rarely speaking of his brother in the years that followed. But grief has a way of surfacing at unexpected times, and the experience of raising his own children, of watching them grow and develop their personalities, may have brought back memories of the brother with whom he had shared a Bristol childhood, the brother who had struggled with their father's demands and expectations just as Paul had, but who had not found the escape into mathematics that had saved Paul from despair. The emotional distance that Dirac maintained from his daughters was perhaps in part a protection against the vulnerability that comes with love, a lesson learned too well in a household where affection was dangerous and connection could be used as a weapon of control. Despite the distractions and difficulties of wartime, Dirac continued to produce theoretical work of considerable importance. In 1941, he published a paper on relativistic wave equations that extended his earlier contributions to quantum mechanics and demonstrated that his creative powers remained undiminished even as he approached his 40th year. The paper explored the mathematical structure of equations describing particles traveling at speeds approaching that of light, building on the foundation of the Dirac equation that he had discovered more than a decade earlier and pushing further into the elegant territory where relativity and quantum mechanics intertwine. This work received less attention than it might have in peacetime, when the physics community would have been more focused on fundamental research, but it represented a continuation of the theoretical program that had occupied Dirac since his earliest days as a physicist, the quest to understand the deepest mathematical structures underlying physical reality. The recognition that Dirac deserved for his wartime contributions and for his lifetime of achievement would come eventually, though it would take many years for some honors to arrive. Much later, in 1973, he would be appointed to the Order of Merit, one of the highest distinctions that the British Crown can bestow, limited to only 24 living members at any time. This honor acknowledged not only his revolutionary contributions to physics but also his service during the war years, when he had applied his remarkable intellect to problems of immediate practical consequence even while maintaining his commitment to the pure and beautiful mathematics that had always been his first love. As the war drew toward its close, with the eventual defeat of Germany and the terrible demonstrations of atomic power over Japan, Dirac could reflect on a period in which the world had changed profoundly and in which his own discipline of physics had been transformed from an abstract pursuit into a matter of the highest national importance. He had played his part, making contributions that were valued by those who understood them, while remaining true to his nature as a contemplative and somewhat solitary thinker. The post-war world would bring new challenges and new opportunities, and Dirac would navigate them in his characteristic way, with patience and precision and an unwavering commitment to the mathematical truth that he had pursued since his earliest days in the quiet rooms of Cambridge. And so we come now to the post-war years, a time when the world of physics was changing rapidly around Paul Dirac, and yet Dirac himself remained as steadfast as ever in his convictions about what constituted proper mathematics and what did not. The Second World War had ended, and with it came a great renewal of activity in fundamental physics, a flowering of new ideas and new techniques that would reshape the field in ways that Dirac found deeply troubling, not because progress was being made, but because of the manner in which that progress was achieved. In the years immediately following the war, three physicists working largely independently of one another developed what would come to be known as renormalized quantum electrodynamics, a framework for calculating the interactions between light and matter with extraordinary precision. Julian Schwinger in the United States, Richard Feynman also in the United States though working in quite a different style, and Shinichiro Tominaga in Japan, each found ways to extract meaningful predictions from the theory of quantum electrodynamics, and their work, which came together between roughly 1947 and 1949, would eventually earn all three of them the Nobel Prize. The problem they addressed was one that had plagued the theory since its inception, the problem of infinities that appeared in calculations whenever one tried to compute certain quantities with any degree of completeness, infinities that seemed to render the theory meaningless or at least unusable for practical purposes. The technique they employed, which came to be called renormalization, involved a rather ingenious if somewhat unsettling procedure. The infinities that appeared in the calculations were, in essence, absorbed into the definitions of physical quantities like the mass and charge of the electron, quantities that one measures experimentally rather than calculates from first principles. By this method, the troublesome infinite terms could be made to cancel out or disappear into measured constants, leaving behind finite predictions that could be compared with experiment. And compare they did, with results of breathtaking accuracy, predictions that matched observations to many decimal places, a triumph of applied mathematics and physical intuition that the broader physics community celebrated with considerable enthusiasm. But Paul Dirac did not celebrate. He watched these developments with growing unease, and as the years passed his dissatisfaction only deepened into something approaching dismay. To Dirac, the procedure of renormalization was fundamentally unsound, a mathematical sleight of hand that papered over deep problems rather than solving them. He described it as sweeping infinities under the rug, a vivid phrase that captured his sense that the theory's practitioners were hiding their failures rather than confronting them honestly. He called it not sensible mathematics, a judgment that for Dirac carried the weight of moral condemnation, for sensible mathematics was to him the highest standard by which any physical theory must be measured. It is worth pausing here to understand why Dirac felt so strongly about this matter, for his objections were not merely aesthetic preferences but reflected his deepest convictions about the relationship between mathematics and nature. Throughout his career, Dirac had believed that the fundamental laws of physics must be expressible in terms of beautiful mathematics, mathematics that was internally consistent, logically rigorous, and free from arbitrary procedures or ad hoc adjustments. The Dirac equation had emerged from just such a commitment to mathematical beauty, and its success had only strengthened his faith that nature rewards those who insist upon elegance. Renormalization, with its cancellation of infinities against other infinities, with its reliance on measured quantities to absorb theoretical embarrassments, seemed to Dirac a betrayal of this principle, a retreat from the high standards that theoretical physics ought to maintain. And so while the rest of the physics community moved forward with renormalized quantum electrodynamics, calculating ever more precise predictions and developing ever more sophisticated techniques, Dirac continued to search for something better, a more elegant formalism that would accomplish the same ends without the mathematical compromises that he found so distasteful. This search would occupy much of his remaining scientific life, though it would not lead him to the breakthrough he sought. During these years, Dirac also turned his attention to questions of cosmology, producing in 1948 a paper that introduced what has come to be known as the Dirac large numbers hypothesis. This idea emerged from his contemplation of certain curious numerical coincidences that appear when one examines the fundamental constants of nature. If one takes the ratio of the electromagnetic force between an electron and a proton to the gravitational force between them, one obtains an enormously large dimensionless number, roughly 10 to the power of 40. And if one expresses the age of the universe in atomic units, using the natural timescale set by atomic physics, one obtains another very large number that is remarkably close to this same value, also roughly 10 to the power of 40. Dirac found this coincidence deeply suggestive, too striking to be dismissed as mere accident. He proposed that these large numbers might be related by some deeper principle, and that as the universe ages and the cosmic timescale grows larger, other supposedly constant quantities might change as well to maintain the relationship. In particular, he speculated that the gravitational constant might vary with cosmic time, growing weaker as the universe expands. This was a bold proposal, for the constancy of the fundamental constants had long been taken for granted in physics, and Dirac was suggesting that at least some of these constants might not be constant at all but might evolve slowly over the vast stretches of cosmological time. The large numbers hypothesis attracted some interest but also considerable skepticism, and later observational evidence would place increasingly stringent limits on any variation in the gravitational constant, limits that appeared to contradict Dirac's speculation. Yet the idea itself, the notion that the fundamental constants might have cosmological significance and might perhaps evolve with the universe, has continued to attract attention from time to time, a reminder that even Dirac's less successful ideas often touched upon deep and unresolved questions. During this period, Dirac continued to travel and to lecture, visiting institutions across Europe and America to present his work and to engage with colleagues. He spent time at the Institute for Advanced Study in Princeton, that remarkable institution where Einstein also resided, a place dedicated to pure research and the unhurried contemplation of fundamental questions. He attended conferences and gave talks, though his reserved manner and his increasingly unfashionable views set him somewhat apart from the younger generation of physicists who were embracing renormalization and moving on to new problems. He also continued to revise his great textbook, The Principles of Quantum Mechanics, which had first appeared in 1930 and which had shaped the education of generations of physicists. The fourth edition appeared in 1958, refined and polished through decades of teaching and reflection, still bearing the distinctive clarity of Dirac's prose, still remarkable for its economy and precision. The book remained in print and in use, a classic of scientific literature that conveyed not only the technical content of quantum mechanics but also something of Dirac's particular way of thinking about the subject, his insistence on logical structure and mathematical elegance. Alongside these activities, Dirac was also pursuing a line of technical research that would prove more lastingly influential than he perhaps realized at the time. He developed a systematic approach to what are called constrained Hamiltonian systems, mechanical systems in which certain constraints must be imposed on the variables, and in doing so he introduced what are now known as Dirac brackets, a generalization of the Poisson brackets that appear in classical mechanics. This work, which unfolded through a series of papers in the 1950s on the quantization of singular Lagrangians, might seem highly abstract and rather removed from immediate physical applications, but it would eventually prove foundational for the development of gauge theories, the class of theories that now describe all the fundamental forces except gravity, and later still for the mathematical framework of string theory. It is one of the curious features of Dirac's career that some of his most influential contributions were not immediately recognized as such, that techniques he developed for their mathematical interest would later turn out to be essential tools for physicists working on problems he himself never engaged with. The Dirac bracket is a case in point, a piece of formalism that sits quietly in the background of much modern theoretical physics, doing its work without fanfare, a testament to the enduring value of careful mathematical groundwork. There is an anecdote from this period, perhaps apocryphal but certainly in keeping with Dirac's character, concerning his opinion of the Feynman diagrams that had become so central to the practice of quantum field theory. These diagrams, invented by Richard Feynman as a way of visualizing and organizing the calculations of renormalized quantum electrodynamics, had proven enormously useful, allowing physicists to compute complicated processes by drawing simple pictures and following systematic rules. When asked what he thought of Feynman diagrams, Dirac is said to have remarked that he found them insufficiently rigorous, that however convenient they might be for calculation, they did not meet his standards for proper mathematical reasoning. Whether or not he used precisely these words, the sentiment was entirely characteristic, a reflection of his unwavering commitment to rigor over convenience, to understanding over mere computation. As the 1950s progressed, Dirac found himself increasingly isolated from the mainstream of theoretical physics. The community had accepted renormalization, had moved on to new problems in particle physics and quantum field theory, and had little patience for what seemed like philosophical quibbles about mathematical foundations. Dirac's objections, however principled, were seen by many as old-fashioned, the complaints of a man who could not accept that physics had changed since his youth. His Cambridge colleagues respected him, of course, and his achievements were beyond question, but his active research was no longer at the center of the field's attention. Among those colleagues at Cambridge during this period were Fred Hoyle, Hermann Bondi, and Thomas Gold, three cosmologists who had proposed the steady-state theory of the universe, an alternative to the Big Bang model that held that the universe had no beginning and no end, that new matter was continuously created to fill the gaps left by cosmic expansion, so that the universe on the largest scales always looked more or less the same. Dirac was somewhat sympathetic to this view, or at least found it interesting, perhaps because it too represented a willingness to question established ideas, a refusal to accept the conventional wisdom simply because it was conventional. The steady-state theory would eventually be abandoned in favor of the Big Bang, but in the 1950s it was still a live option, and Dirac's openness to it reflected his continued engagement with fundamental questions about the nature of the cosmos. And so we leave Dirac in this period of his life, still working, still thinking, still searching for the elegant mathematical truth that he believed must underlie the physical world, even as that world moved in directions he could not follow. He had not given up his convictions, had not made peace with renormalization, had not accepted that sweeping infinities under the rug was an acceptable way to do physics. In this stubbornness there was something admirable, a refusal to compromise on matters of principle, even if it meant standing alone. Whether history would vindicate his concerns, whether some future theory would achieve the elegance he sought without the compromises he deplored, remained to be seen. For now, he continued his quiet work, patient and unhurried, trusting in the mathematics that had guided him all his life. In the year 1960, Paul Dirac was 58 years old, and though he remained the Lucasian Professor of Mathematics at Cambridge, a position he had held since 1932, he had begun to accept visiting appointments at various American universities, drawn perhaps by the warmth of different climates and the opportunity to continue his research away from the administrative pressures that had slowly accumulated around him in England. These visits were quiet affairs, as one might expect from a man of his temperament, and they took him first to the University of Miami, where the subtropical air and gentle breezes off Biscayne Bay offered a marked contrast to the perpetual grey dampness of the Cambridgeshire fens, and later to Yeshiva University in New York, where he delivered lectures and worked on his equations in borrowed offices, always maintaining the same unhurried routine that had characterized his entire working life. He also spent time at Florida State University in Tallahassee, a city situated in the Panhandle region of Florida, where the climate was warm but not quite so humid as the southern coast, and where the university had been steadily building its physics department with an eye toward attracting distinguished scholars. These visiting positions allowed Dirac to test, in a sense, what life might be like away from Cambridge, away from the college dinners and the committee meetings and the endless damp cold that seeped into his bones during the long English winters, and gradually, over the course of the 1960s, the idea of leaving England altogether began to take shape in his mind, though he mentioned it to very few people and made no dramatic announcements about his intentions. The Lucasian Chair of Mathematics at Cambridge is one of the most ancient and prestigious positions in all of academic science, having been established in 1663 and held over the centuries by such luminaries as Isaac Newton and Charles Babbage, and Dirac had occupied this chair for 37 years. A tenure of remarkable length during which he had transformed the landscape of theoretical physics and trained, in his quiet and somewhat unconventional way, a generation of younger physicists. But in September of 1969, at the age of 67, Dirac retired from the Lucasian professorship, stepping down from the position that had been his intellectual home for nearly 4 decades. The university held the appropriate ceremonies and acknowledgements, as institutions do, but Dirac himself seems to have regarded the transition with his characteristic equanimity, neither celebrating the milestone nor expressing particular regret about leaving. He had never been sentimental about such things, and his attention remained fixed, as it always had been, on the equations and the deeper structures of the physical world that continued to occupy his thoughts. Retirement from Cambridge did not mean, for Dirac, a retreat into idleness or leisure, for he had no interest in the conventional pursuits of retired persons and no intention of abandoning the work that had given shape and meaning to his entire adult life. Instead, in 1971, he accepted a position as professor of physics at Florida State University in Tallahassee, an appointment that carried with it generous terms and minimal administrative responsibilities, allowing him to continue his research and teaching without the burdens that had increasingly weighed upon him in England. The offer from Florida State was attractive for several reasons, not least of which was the promise of warm sunshine and dry air, conditions that suited Dirac's constitution far better than the damp cold of Cambridge, which had troubled him for many years and which he found increasingly difficult to bear as he grew older. Margit, too, welcomed the change, for she had always been more sociable than her husband and found the prospect of a new home in a warm climate agreeable, and so in 1971 the Diracs made their move across the Atlantic, leaving behind the grey stone buildings and the ancient traditions of Cambridge for the pine forests and gentle hills of northern Florida. They settled into a modest home at 223 Chapel Drive in Tallahassee, a comfortable but unpretentious house that suited their needs and their temperament, and there Margit set about planting a garden, bringing color and life to the Florida soil while her husband continued his daily routine of mathematical work. The house was not grand, for Dirac had never been interested in material display, and its simplicity reflected the same aesthetic that had guided his approach to physics throughout his career, the same conviction that elegance lay in simplicity and that unnecessary ornamentation was to be avoided. The neighborhood was quiet, the neighbors friendly but not intrusive, and the pace of life in Tallahassee was unhurried in a way that suited the elderly physicist perfectly. Margit's garden flourished in the Florida sunshine, producing flowers and vegetables that she tended with care, and one imagines that Dirac, returning home from his office in the late afternoon, would have passed by these growing things with his usual measured pace, perhaps noticing them, perhaps not, his mind occupied with other matters entirely. His reasons for leaving England were practical rather than emotional, as most of his decisions tended to be. The weather, first and foremost, had become intolerable to him, for Cambridge's damp cold affected his health and his spirits, and the prospect of spending his remaining years in warmth and sunshine was genuinely appealing. The generous terms offered by Florida State University meant that he could continue his work without financial worry and without the administrative entanglements that had multiplied at Cambridge over the years, and the relative obscurity of Tallahassee, compared to the constant attention and formality of Cambridge, offered a kind of freedom that he valued. He had never enjoyed being the center of attention, had never sought recognition for its own sake, and in Florida he could work quietly, surrounded by colleagues who respected his privacy and students who were eager to learn from him but who did not presume upon his time. There was also, perhaps, something liberating about starting fresh in a new place at the age of 69, leaving behind the accumulated weight of decades and beginning again in simpler circumstances, though Dirac himself would probably not have described it in such terms, preferring instead to cite the practical advantages and leave the matter at that. His daily routine at Florida State University was much the same as it had always been, for Dirac was a man of fixed habits who found comfort in regularity and repetition. He would arrive at his office in the morning, settle into his chair, and begin working on equations, filling pages with his neat handwriting as he pursued whatever problem had captured his attention at the moment. His conversations with colleagues were minimal, not from any hostility or unfriendliness but simply because he had little to say about matters unrelated to physics and saw no reason to engage in small talk for its own sake. When he did speak, his words were precise and carefully chosen, and his colleagues learned to listen attentively because nothing he said was superfluous. He would take his lunch alone or with Margit if she happened to be nearby, and then he would return to his office and continue working until the late afternoon, when he would walk home through the warm Florida air, his steps slow and deliberate, his mind still turning over the problems he had been considering all day. His lectures at Florida State University were occasions of considerable interest for the students and faculty who attended them, for here was one of the founders of quantum mechanics, one of the greatest theoretical physicists of the 20th century, standing before them and explaining the principles of general relativity and quantum mechanics in his distinctive quiet voice. He spoke from sparse notes, having prepared his lectures carefully but having no need for extensive written material, and his delivery was unhurried and methodical, each sentence following logically from the one before, each concept explained with precision and clarity. The students found him intimidating, as students often do when confronted with genius, but they also found him inspiring, for there was something in his absolute dedication to understanding the physical world that communicated itself even through his reserve, and those who were willing to engage seriously with the material discovered in Dirac a teacher of remarkable depth. He did not encourage questions during his lectures, preferring to proceed through his material without interruption, and students quickly learned that he was not inclined to digress or to offer encouragement beyond the material itself. There is an anecdote from this period that captures something essential about Dirac's approach to discourse, an exchange that occurred during one of his lectures at Florida State University and that has been repeated many times since by those who witnessed it or heard about it later. A student, emboldened perhaps by curiosity or confusion, raised a hand and made a statement about some aspect of the material being presented, expecting Dirac to respond with clarification or comment. Dirac, however, remained silent, standing at the front of the room and making no acknowledgement of the student's words, and the silence stretched on for what must have felt like a very long time to everyone present. Finally, someone in the room prompted him, perhaps suggesting that the student had asked a question, whereupon Dirac replied simply that it was not a question but rather a comment, and he continued with his lecture as if nothing had happened. The exchange illustrates perfectly Dirac's literal-mindedness and his refusal to engage with anything imprecise or unnecessary, for in his view a question required a question mark, and a statement, however interrogative in tone, was merely a statement to which no response was required. Those who knew him well understood this about him and did not take offense, recognizing that his silence was not rudeness but simply the expression of a mind that processed language differently from most. Throughout his years at Florida State University, Dirac continued to publish papers and deliver lectures on the topics that had concerned him for decades, and among these topics was his continued criticism of the technique known as renormalization, which had become standard practice in quantum field theory but which Dirac regarded as mathematically unsatisfactory and fundamentally flawed. Renormalization is a procedure by which the infinities that arise in quantum field theory calculations are systematically removed, allowing physicists to make predictions that agree remarkably well with experimental observations, and it has been enormously successful in practical terms, forming the foundation of the standard model of particle physics. But Dirac could not accept a procedure that involved subtracting infinities from infinities to obtain finite results, no matter how well it worked in practice, for it offended his sense of mathematical beauty and seemed to him a temporary expedient rather than a true solution. In paper after paper, and lecture after lecture, he argued against renormalization, insisting that a proper theory of quantum electrodynamics must be found that does not require such manipulations, and though his criticisms were respected, they did not sway the majority of physicists, who continued to use renormalization techniques with great success. Dirac was not deterred by this, for he had never been swayed by majority opinion and had always followed his own mathematical instincts regardless of what others thought. His eccentricities remained with him throughout his later years, small particularities of behavior that those who knew him came to expect and even to cherish. Among these was his refusal of a knighthood, which had been offered to him in 1953 but which he had declined, not from any lack of patriotism or respect for the honor but simply because he did not wish to be addressed by his first name. The title of Sir would have required that he be called Sir Paul, and Dirac, who had always been reserved about personal matters and uncomfortable with familiarity, found this prospect disagreeable. It was a curious reason for refusing such an honor, but it was entirely consistent with his character, and those who knew him understood that it was not false modesty or any deeper objection but simply a practical dislike of the way the title would have been used. He remained Professor Dirac, or simply Dirac, throughout his life, and this suited him perfectly well. In 1973, however, he did accept a different honor, the Order of Merit, which was conferred upon him in recognition of his extraordinary contributions to science. The Order of Merit is one of the highest honors in the gift of the British sovereign, limited to only 24 living members at any one time, and it does not carry with it the requirement that the recipient be addressed by his first name, which perhaps made it more acceptable to Dirac than a knighthood would have been. The honor was richly deserved, for by 1973 Dirac had been recognized for decades as one of the greatest physicists of his generation, and the Order of Merit simply confirmed what the scientific community had long known. He accepted it quietly, as he accepted most things, without fanfare or ceremony, and returned to his equations and his lectures, continuing the work that had occupied him for more than 50 years. And so his life in Florida continued, day following day in the warm sunshine, the garden growing and blooming outside the modest house on Chapel Drive while inside, or in his office at the university, Dirac pursued his equations with the same dedication that had characterized his entire career. The move to America had been a good one, providing him with the conditions he needed to continue working in peace, surrounded by colleagues who respected his genius and his privacy, and he settled into these final years with something approaching contentment, or at least with the absence of discontent, which for Dirac may have amounted to much the same thing. In the early 1970s, Paul Dirac settled into what would become the final chapter of his remarkable life, a period marked by continued intellectual engagement even as the body that housed his extraordinary mind began its slow and inevitable decline. He was now approaching 70 years of age, and though he had officially retired from his position at Cambridge some years earlier, he remained active in the way that suited him best, which is to say quietly, methodically, and with an unwavering commitment to the questions that had occupied him for half a century. The move to Florida State University had given him a new institutional home, a place where the warm climate agreed with his aging constitution and where he could continue his work without the administrative burdens that had never suited his temperament. During these years, Dirac returned repeatedly to certain themes that had fascinated him since his youth, ideas that he felt had never received the attention they deserved from the broader physics community. Chief among these was his large numbers hypothesis, that curious observation about the ratios between fundamental constants of nature, ratios that seemed to cluster around powers of an extraordinarily large number, approximately 10 to the power of 40. Dirac had first noticed this apparent coincidence decades earlier, and he never stopped wondering whether it might point toward some deeper truth about the structure of the universe. He published papers exploring this hypothesis throughout his 70s and into his early 80s, papers that were received with polite interest by his colleagues but which never quite achieved the influence of his earlier work. This did not seem to trouble him greatly, for he had long since made his peace with the fact that many of his ideas would take time to be appreciated, if indeed they ever were. The question of magnetic monopoles also continued to occupy his thoughts, and in 1973 he published a paper that returned to this subject with fresh arguments and renewed conviction. He had first predicted the possible existence of these hypothetical particles in 1931, reasoning from first principles that if magnetic monopoles existed, they would explain why electric charge appears in nature only in discrete quantized units. More than 4 decades later, he remained convinced that these particles must exist somewhere in the universe, even though no experiment had ever detected one. His 1973 paper offered new theoretical perspectives on the matter, and it is a testament to his intellectual vitality that he could still find something original to say about a topic he had been contemplating for over 40 years. To this day, physicists continue to search for magnetic monopoles, and though they remain elusive, Dirac's original arguments for their existence have never been refuted. In 1975, Dirac published what would be his final book, a slim volume titled General Theory of Relativity. The book was characteristically concise, spanning only 6 to 9 pages in its entirety, and it presented Einstein's theory of gravitation with the same economy and elegance that had marked all of Dirac's written work. Where other authors might have taken hundreds of pages to cover the same material, Dirac distilled the essential mathematics and physics into their purest form, stripping away everything unnecessary until only the fundamental structure remained. The book was not intended to be a comprehensive treatment of the subject, nor did it contain any new research, but it served as a beautiful example of how a master physicist approaches the exposition of difficult ideas. Students who encountered this book often remarked on its clarity and its uncompromising mathematical precision, qualities that reflected Dirac's lifelong belief that physical theories should be beautiful first and foremost. As Dirac moved through his 70s, he maintained a relationship with younger physicists that might best be described as one of respectful distance, though on occasion a genuine warmth would emerge from behind his habitual reserve. He was not the sort of mentor who took students under his wing or engaged in lengthy collaborative discussions, but those who had the opportunity to interact with him often came away with a profound impression of his intellectual integrity and his deep commitment to the pursuit of truth. At the 1978 International Symposium on Mathematical Physics in Rome, Dirac delivered lectures that reminded the assembled physicists of his continued engagement with the field, and his presence at such gatherings was always treated with a certain reverence, for he represented a living connection to the revolutionary generation that had created quantum mechanics. Throughout these years, Dirac maintained one position with remarkable consistency, a conviction that he expressed to anyone who would listen and that he never abandoned despite the overwhelming practical success of the theory in question. He believed that quantum electrodynamics, the theory that describes how light and matter interact, was fundamentally flawed and would eventually need to be replaced by something more beautiful. The renormalization techniques that had been developed in the late 1940s to make the theory's predictions finite struck him as mathematically ugly, a kind of sleight of hand that swept genuine problems under the carpet rather than solving them. The fact that these techniques produced predictions of extraordinary accuracy, matching experimental results to many decimal places, did not impress him in the slightest, for he had always believed that mathematical beauty was a more reliable guide to truth than mere agreement with experiment. He never recanted this view, never acknowledged that perhaps the success of quantum electrodynamics might indicate that his aesthetic objections were misplaced, and he went to his grave convinced that a more elegant theory awaited discovery by future generations. In 1978, the artist Michael Noakes painted a portrait of Dirac, capturing the physicist in his 8th decade of life. The portrait showed a man whose features had grown gaunt with age but whose eyes retained something of the intensity that had characterized his younger self. Dirac sat for the portrait with his usual patience, and the resulting work now serves as one of the lasting visual records of how he appeared in these final years. The matter of Dirac's family remained complicated even in old age, shaped by the wounds of his difficult childhood and by his own lifelong struggles with emotional expression. He and his sister Beatrice had grown apart many years earlier, and by this period of his life they rarely spoke at all. The reasons for this estrangement were never fully explained by either party, but it seems likely that the shared trauma of their childhood under their father's rigid and emotionally cruel regime had affected them differently, leaving them unable to find common ground as adults. Dirac almost never spoke of his father during these years, and when the subject came up, he would acknowledge only the damage that had been done, offering no softening of his judgment and no retrospective understanding of the man who had shaped his early life in such painful ways. He had concluded long ago that his father's treatment of him had been harmful, and he saw no reason to revisit that conclusion or to search for extenuating circumstances. With his own children and grandchildren, however, Dirac made what might be described as awkward but genuine attempts to be a better presence than his own father had been. He was never going to become a warm and effusive patriarch, for that was simply not in his nature, but there were moments of connection, small gestures that suggested he understood the importance of family even if he could not always express it in conventional ways. His wife Margit remained his constant companion through these years, and she devoted herself to his care with a tenderness that had characterized their relationship from the beginning. She understood him in ways that few others did, accepting his silences and his eccentricities as part of the man she had married, and as his health began to decline, she was there to provide both practical assistance and emotional support. The early 1980s brought a gradual deterioration in Dirac's physical condition. His daily walks, which had long been a part of his routine and which he had always valued for the opportunity they provided for quiet contemplation, became shorter as his strength diminished. He continued to work as best he could, continued to think about the problems that had occupied him for so long, but the body was making its demands known in ways that could not be ignored. Yet even as his health faded, honors continued to accumulate. In 1982, Cambridge University established the Dirac Memorial Lecture Series in his honor, a recognition that his contributions to physics would be remembered and celebrated for generations to come. It was perhaps a strange experience to receive such a memorial while still alive, but Dirac accepted the honor with his characteristic quietness. During these final years, Dirac continued to reflect on the nature of the universe and on the mathematical structures that seemed to underlie all of physical reality. He had long believed that mathematics was not merely a tool invented by humans to describe nature, but was instead something more fundamental, a language that the universe itself seemed to speak. He expressed this conviction in a phrase that has since become one of his most famous utterances, observing that God is a mathematician of a very high order, and that God used very advanced mathematics in constructing the universe. This was not a statement of religious belief in any conventional sense, for Dirac had never been a religious man, but it captured something of his sense of wonder at the mathematical harmony he had discovered in his work, a harmony that seemed too perfect to be accidental. In 1984, Dirac submitted what would prove to be his final scientific paper, a last contribution to the literature of physics from a man who had been publishing for nearly 60 years. He was 81 years old, and though his powers had diminished from their peak, the act of completing and submitting a paper represented a kind of continuity with the work that had defined his life. He had been a physicist from his early 20s, and he would remain a physicist until the very end. The quiet twilight of Paul Dirac's life was not a time of dramatic events or sudden revelations, but rather a gradual dimming of the light, a slow settling into stillness after decades of profound intellectual activity. He had never sought fame or public attention, had never cultivated the sort of personality that would make him a celebrity even within the world of science, and in his final years he remained true to that essential character. He thought about physics, he worried about the future of theories he considered flawed, he accepted the care of his devoted wife, and he waited with his usual patience for whatever came next. The contributions he had made to human understanding of the universe were secure, preserved in textbooks and in the ongoing work of physicists around the world, and though he might have wished for more time to pursue the questions that still interested him, he had already done more than most people could accomplish in several lifetimes. The equation that bore his name would continue to describe the behavior of electrons long after he was gone, and the principle of antiparticles that he had predicted would remain a cornerstone of physics for as long as the science itself endured. On the 20th of October, in the year 1984, Paul Adrien Maurice Dirac passed away quietly in Tallahassee, Florida, the city that had become his home in the final decades of his life, and the cause of his death was kidney failure, a gradual decline that had been some time in its progression, and he was 82 years old when he died, having lived long enough to witness many of the consequences of his theoretical work unfold in laboratories and accelerator facilities around the world, though he had also lived long enough to see physics move in directions that he found troubling, with methods he could not bring himself to embrace, and so his passing marked the end of a particular way of doing theoretical physics, a way that prized elegance and economy above all else, and that trusted in the harmony between mathematics and nature as a guiding principle for discovery. He was buried at Roselawn Cemetery in Tallahassee, a peaceful resting place far removed from the ancient university towns of Cambridge and Göttingen where he had done his most celebrated work, and far removed too from Bristol where he had spent his difficult childhood in the shadow of his demanding father, and there is something fitting perhaps in the fact that he came to rest in this quiet corner of Florida, because Dirac had always been a man who sought quietude, who preferred the stillness of thought to the bustle of academic life, and who had found in the warmth and relative seclusion of Tallahassee a congenial environment for his final years, even as his health declined and his ability to pursue new research diminished. His wife Margit survived him by nearly 2 decades, and she continued to live in Tallahassee, maintaining the memory of her husband and occasionally corresponding with physicists and historians who wished to understand the man behind the equations, and Margit Dirac passed away in 2002, having outlived not only her husband but also the century in which they had met and married, and her death brought to a close the immediate family chapter of Dirac's story, though his intellectual legacy had by then become something quite separate from any individual life, a legacy that belonged to the entire community of physicists and mathematicians who used his methods and contemplated his ideas. More than 11 years after Dirac's death, on the 13th of November in 1995, a memorial service was held at Westminster Abbey in London, that ancient church where so many of the great figures of British history are commemorated, and during this service a commemorative stone was placed in the nave of the abbey, positioned near the grave of Isaac Newton, which seemed entirely appropriate given that many regarded Dirac as the greatest British theoretical physicist since Newton himself, and the stone was inscribed with the Dirac equation in its compact and beautiful form, that deceptively simple arrangement of symbols that had revealed the existence of antimatter and explained the intrinsic spin of the electron, and it was perhaps the first time that a mathematical equation had been carved into the floor of Westminster Abbey as a memorial, which tells you something about the singular nature of Dirac's contribution to human understanding. The equation inscribed on that stone, sometimes written in the form where the operator involving partial derivatives and gamma matrices acts upon the wave function to produce a term proportional to the mass, is considered by many physicists to be one of the most beautiful equations in all of science. And beauty is not a word that scientists use lightly or without consideration, but in the case of the Dirac equation the term seems genuinely warranted, because here was an equation that emerged from the requirement of mathematical consistency, from the demand that quantum mechanics and special relativity be reconciled with one another, and yet from this purely formal requirement there emerged predictions about the physical world that no one had anticipated and that were subsequently confirmed by experiment, including the existence of positrons and the precise value of the electron's magnetic moment. The Dirac equation predicted that electrons must have an intrinsic angular momentum, a spin of 1/2 in natural units, which had been observed experimentally but never before explained from first principles, and the equation also predicted that electrons must have a magnetic moment of a particular strength, and when experimenters measured this quantity they found that the Dirac equation's prediction was accurate to a remarkable degree, though later corrections from quantum electrodynamics would refine the prediction even further. And beyond these confirmations, the equation contained within its mathematical structure a prediction that was entirely unexpected, namely the existence of particles with the same mass as the electron but with opposite electrical charge, which we now call positrons or anti-electrons, and which were discovered by Carl Anderson in 1932, just a few years after Dirac had written down his equation. The notation that Dirac introduced for quantum mechanics, the bracket notation as it is commonly called, has become the standard language in which quantum mechanical calculations are expressed, and if you were to open any modern textbook on quantum mechanics or attend any lecture on the subject at any university in the world, you would find this notation being used as naturally and unremarkably as ordinary algebraic notation is used in other branches of mathematics, And this universality is a testament to the clarity and utility of Dirac's approach, because he had a gift for finding the right way to express things, the way that made calculations simpler and relationships more transparent, and his notation allowed physicists to manipulate the abstract objects of quantum mechanics with confidence and efficiency. The Dirac delta function, though it was not invented by Dirac in a strict mathematical sense, was developed and popularized by him as a tool for handling certain calculations involving continuous spectra and orthogonality relations, and mathematicians initially regarded this object with some suspicion because it was not a function in the conventional sense, being zero everywhere except at a single point where it was infinite, yet having a finite integral, which seemed paradoxical or even nonsensical. But later developments in the theory of distributions by mathematicians such as Laurent Schwartz provided a rigorous foundation for what Dirac had been doing intuitively all along, and the delta function is now an indispensable tool not only in physics but in many branches of pure and applied mathematics. The Fermi-Dirac statistics that Dirac developed, in work that overlapped with the independent contribution of Enrico Fermi, governs the behavior of particles with half-integer spin, the particles we now call fermions, and this statistical law is fundamentally different from the Bose-Einstein statistics that governs particles with integer spin, and the distinction between these two types of particles, which follows from the symmetry properties of their wave functions, has profound consequences for the structure of matter, because it is the Fermi-Dirac statistics and the associated Pauli exclusion principle that prevents electrons from all collapsing into the lowest energy state and thereby gives rise to the shell structure of atoms and the rich variety of chemical behavior that makes life possible. The Dirac sea, though it has been superseded by more sophisticated formulations of quantum field theory, was a conceptually important step in understanding how particles and antiparticles are related, and even though physicists no longer think of the vacuum as a sea of negative energy electrons, the ideas that Dirac was grappling with, concerning the nature of the vacuum state and the relationship between particles and holes, continue to resonate in modern theoretical physics, particularly in condensed matter systems where the analogy between electrons and holes in a semiconductor bears a family resemblance to Dirac's original conception. The influence of Dirac on subsequent generations of theoretical physicists is difficult to overstate, and among those who acknowledged a particular debt to his work was Richard Feynman, who credited a paper that Dirac wrote in 1933, concerning the role of the Lagrangian in quantum mechanics, as the inspiration for his own development of the path integral formulation, which became one of the most powerful and versatile approaches to quantum theory and quantum field theory. And Feynman described how he had read Dirac's paper and wondered whether a certain proportionality that Dirac had mentioned could be made into an equality, and from this wondering he developed an entirely new way of thinking about quantum mechanics, which shows how a single suggestive remark by Dirac could open up whole new territories for exploration. Julian Schwinger, who shared the Nobel Prize with Feynman and Tominaga for the development of quantum electrodynamics, was also deeply influenced by Dirac's work, as was John Wheeler, who collaborated with Feynman and made fundamental contributions to general relativity and quantum gravity, and indeed it would be difficult to find a theoretical physicist of the mid-20th century who was not in some significant way shaped by Dirac's ideas and methods, because his textbook on quantum mechanics, The Principles of Quantum Mechanics, was for many years the standard advanced treatment of the subject and trained generations of physicists in a particular way of thinking about quantum theory. Dirac famously insisted that mathematical beauty should be a guiding criterion in the search for physical laws, and he expressed this conviction in various forms throughout his career, suggesting that a theory with mathematical beauty is more likely to be correct than an ugly one, even if the ugly theory appears to have better agreement with experiment at a given moment, because he believed that discrepancies with experiment could be resolved as experimental techniques improved. But a fundamental lack of beauty in a theory was a sign that it was not on the right track, and this aesthetic philosophy was controversial then and remains controversial now, because it is difficult to define precisely what mathematical beauty consists in, and yet many of the great theoretical advances of the 20th century, including Dirac's own work, seem to support the idea that elegance and truth are somehow connected. There is a certain irony in the fact that the technique of renormalization, which Dirac regarded as ugly and fundamentally unsatisfactory, proved to be essential for the construction of the standard model of particle physics, which is our most successful theory of the fundamental forces and particles, and the triumphs of the Standard Model, including its precise predictions for the properties of the W and Z bosons, the existence and mass of the Higgs particle, and countless other experimental confirmations, all depend on renormalization methods that Dirac could not accept, and so the physics community proceeded in a direction that Dirac found distasteful, and achieved great success thereby, though there are still physicists who share Dirac's unease and wonder whether renormalization is perhaps a stopgap method that will eventually be replaced by something more fundamental and more beautiful. The Dirac Medal, established in 1985 by the International Center for Theoretical Physics in Trieste, just 1 year after Dirac's death, is awarded annually to physicists who have made significant contributions to theoretical physics, and the list of recipients reads as a catalogue of the most distinguished theorists of the late 20th and early 21st centuries. And the existence of this medal ensures that Dirac's name continues to be spoken and his memory honored in the physics community, though of course his real memorial is not any medal or stone but the living body of knowledge that he helped to create. The biographical literature on Dirac has grown considerably since his death, and 2 works in particular deserve mention for anyone who wishes to understand his life and work more fully, the first being the scientific biography by Helga Krah published in 1990, which provides a detailed and scholarly account of Dirac's physics and its context, and the second being the more personal biography by Graham Farmelow entitled The Strangest Man, published in 2009, which draws on extensive archival research and interviews to paint a portrait of Dirac as a human being, including his difficult relationship with his father, his struggles with social interaction, and his gradual emergence into a warmer and more connected life through his marriage to Margit and his relationships with his stepchildren and later his own children. And so we come to the question of Dirac's standing in the history of physics, and while such rankings are always somewhat artificial and dependent on the criteria one chooses to emphasize, there is a strong case to be made that Paul Dirac was the greatest British theoretical physicist since Isaac Newton, and if we confine ourselves to the 20th century, he stands alongside Einstein, Bohr, and Heisenberg as one of the supreme figures of the quantum revolution, and his combination of technical virtuosity, conceptual originality, and aesthetic sensibility was perhaps unmatched among his contemporaries, and the equations and methods and notations that bear his name have become so thoroughly woven into the fabric of modern physics that it is difficult to imagine the subject without them, and so his legacy endures, not as a monument but as a living tradition, carried forward by each new generation of physicists who learn to write bras and kets, who marvel at the elegance of the Dirac equation, and who perhaps pause sometimes to reflect on the quiet man from Bristol who saw so deeply into the mathematical structure of nature.